One, two. One, two. One, two. One, one. One, two. One, one. One. Mic check. One, two.
Um, Remember, today we've got a split session. So this is the main session, and then there will be the other one on the fourth floor. So it's already set up, and then I think some of the speakers are up there. So we'll be starting here in 2 minutes' time. We've got a new chairperson, Henry. Thank you. Henry, take over. We cannot delay because we've got 2 sessions.
Okay, thank you very much, and good morning, and you are welcome to this session. I think we have a couple of presentations here. The first will be by Sitnikov Andrei. He'll be presenting on the IAEA activities. So please, if you're ready, you have the floor. Thank you.
Thank you. Good morning. Looks like not easy morning for some of people, yeah. I think it's due to very nice music yesterday. Okay, let's start. My presentation will be about the project which cover new research reactors, capacity building and development of nuclear infrastructure. Before I come to the presentation, I will demonstrate you some environmental scan. I could say at the moment this is actual what we have. Only you can find in different presentations of the agency a little bit different numbers, but this is because we use different sources. This is some kind of summary from our database and from information which come to countries, not via database. Yeah, as you can see, at the moment in the world about 41 new research reactors in different stages. Green, you can see this is stages of implementations. In blue, this is preparatory work, and in red, these considerations. And I don't want to spend time on this. You can find it later in my presentation. Presentation is very long, but I hope it will be 20 minutes enough for this. Interesting picture. It's like some changes in my slide. Anyway, good. As you can see, the environmental scan for Africa here. In operation reactors in green, in gray, this is temporary shutdown. In rose, formal plans. At the moment, it's like Nigeria, South Africa, and Zambia. I could say, in fact, Nigeria not far from start of construction. Yeah, there is sunny. Okay, and a lot of countries thinking about research reactor programs. I could say that 2 years ago, the situation was another one, but due to the problems with transportation of radioisotopes during pandemic period, many countries took decision to construct own research reactors. Now, the place of African countries in activities of our project relative to capacity building. As you can see, a lot of African countries participate in our meetings, training workshops, research reactor school, etc. As well, you see INRIR missions here. Formally, The name of the project is Access to Research Reactors, Capacity Building, and Infrastructure Development. And three main targets of this project: to support member states in planning and implementing new research reactor projects and programs. It means include assessment and development of their national nuclear infrastructure, very important issue, because this is responsibility of the country, not of vendor. Second target is to support member states in building and or preserving national nuclear capacity, including human resource development by using research reactors. And this is not only for newcomer countries, but for experienced countries as well. And third one, I could say 4 years ago, there was serious meeting with high-level African representatives, and we discussed that there are possibilities to use opportunities from neighbor countries, and we include into the project third target: to facilitate member states' access to research reactors for the development of nuclear science technology programs, including nuclear power. Speaking about internal collaboration, Ruben just demonstrated the picture in his slide. That is why I skip it. The nature of nuclear infrastructure means 19 areas. Due to a lot of different questions, and these areas, we have communications, in fact, with a lot of structures inside the agency, as you can see, with an SNI, an IPC, an SNS, etc. I don't want to spend time on this. As well, we have external collaboration and cooperation with national authorities like Atomic Energy Commissions, regulatory body, universities, technical support organizations, etc. With TC projects, national liaison officers and national stakeholders, with regional coalitions like ICER, IRL stakeholders, and with international experts. Major activities as usual for the agency include technical meetings, training workshops, peer review and expert missions, support of research reactor information resources, like, for example, database of research reactors, and different kind of publications relative to our tasks. Speaking about near-RR missions, I could say this is one of the most important part of the project, because it means independent peer review of status of nuclear infrastructure in the country. As you can see, guidance and assistance in development of national infrastructure, assistance in preparation of feasibility study, and self-assessment of nuclear infrastructure. As well, we can include here strategic plan and preliminary evaluation of potential sites, and assistance in human resource development and capacity building. Later I'll say a little bit more about human resource development. Maybe somebody don't know this picture. This is milestones approach of the agency. I don't want to spend a lot of time on this. What is important, you can see here, there is a research reactor program, and there are two lines. One line, the bottom, this is development of research reactor project, and higher line, this is development of nuclear infrastructure. Speaking about project, you can communicate with vendor will come, you pay money, and they will construct research reactor. No serious trouble, in fact, because a lot of research reactors in the world. But especially for newcomer countries, establishment of nuclear infrastructure, this is very high responsibility of the country, of the government. This is serious part of national position, and this is, I could say, ownership of the country, not vendor. Vendor can help you in some cases, but usually vendor, why do it? Because mitigate own risks. And we don't work with vendors, we work with countries. This is, we don't know, for example, who help you in developing some of issues of infrastructure. We working with you, and this is your obligations to establish this, because nuclear infrastructure, this is friendly requirement in the environment of your research reactor for safe, secure operating of your research reactor for a long period of time. Objective of missions, as you can see, provide assistance in determining the status of national nuclear infrastructure, identify further development needs to support new research reactors. It means we clarifying gaps, allow all research reactor infrastructure issues to be assessed in equal and consistent manner, and create a space for sharing experience and good practices. And I need to say that we come into countries not to criticize it. We come in to work together to understand what is necessary to do, what kind of gaps necessary to cover due to their existence. Yeah. Benefits of a neural mission, I think it's very clear. The main idea is this is independent review by international experts. And when we prepare the team of experts, we very serious about conflict of interests, no any impacts from different providers of technology or vendors. That is why I could say it can be very useful for countries. Undertaken missions. First mission was like pilot in Nigeria in 2018. The same year, second mission was in Vietnam. In December 21, it was Thailand, and we conducted 2 follow-up missions, one in 22nd in Nigeria, and in April, May 24 in Thailand. The last mission for phase 1 was in Kenya in 2023. You see how many high-level representatives been there, a lot of, I could say, representative of government, some ministers, or vice ministers, etc. And it was a lot of discussions, and I very hope that the mission was successful. Hilda can share with you experience of their mission if you need. Hilda, where you are? Upstairs. Good, thank you. Peer review missions plans. For phase 2, we start in phase 2, and it will be again pilot mission in Nigeria in February of next year. Sorry, Uganda should be in phase 2. This is my technical mistake, yeah. For this year, we planned 2 missions to Uganda and Rwanda, but during the general conference, we discussed and found that better to do it next year, yeah. We have official request. It means for any phase 2, it will be Nigeria and possibly Vietnam. As well, it may be Kenya follow-up and phase 2. We just discussed this issue. Speaking about phase 1, we'll plan for next year Rwanda, Uganda, Senegal, and Ethiopia. Now about meetings and trainings. We have, I could say, regular 4 training workshops. Milestones, preparation of feasibility study, preparation of bids, and self-assessment of nuclear infrastructure. Every year we have 2 workshops, and we repeat this every 2 years. Again, this is the role of Africa in our training workshop. You see, it's very active. A lot of countries participate. I will skip these slides to save our time. Yeah. In 22nd, you can see numbers, how many people from how many countries. I could say the half of countries are from Africa. Training workshop of human resource development for research reactor program in Senegal. Later we will discuss this. I have 2 more slides on this. Regional meeting for milestone approach for research reactor project. It was in Zambia. We discussed with TC some time ago, and TC clarified 2 projects for Africa, regional project RAF 1009. This is for 8 newcomer countries, and 1010 for experienced countries. And this meeting was requested by 8 countries of newcomers, and looks like it was successful because during the week we delivered a lot of presentations and we had a lot of discussions about how to develop research area program. This is about Malaysia. Malaysia organized huge meeting with potential stakeholders, utilization stakeholders, and stakeholders of public acceptance. and we discussed with them advantages and troubles relative to research reactor programs. Yulia is here, and again, if you would like to understand how it's happened, you can discuss with Yulia. She can explain. Next one, assessment of nuclear infrastructure. In 23, then technical meeting of human resources. Later, say in more detail, it was a very important meeting. We installed new software for plans, national plans of human resources, because this is one of the most serious challenge before you take a decision about at the end of phase 1 about continuing of your research reactor program. And we discussed and prepare new activity, and this meeting clarified, made some clarification and justification of how the model is working, and we found that precision is very high, about 85%, and we were surprised that in different countries approach for human resources very similar for different kind of reactors, but similar. And speaking about the stuff of nuclear research reactors and the stuff of facilities and the rest of research reactor program. Then training workshop of preparation of feasibility study, bidding process. During training workshop of bidding process, usually we organize some kind of exercise. We make 2, 3, 4 groups and give them the task, and they prepare in some kind of temporary bidding specification, and later we will discuss together advantages and disadvantages of their work. In April of this year, assessment of nuclear infrastructure. Many people were online due to some the room was not so big. In fact, yeah, this is one of troubles of the agency. As a result, some people did not attend, but they participate virtually. You see 55 participants from 23 member states, and we found new people and new countries come to us, like, for example, Zimbabwe and Togo, as I remember. In August, we have training workshop on milestones of research reactor project. Yes, it was in August. 75 participants from 48 member states. Again, a lot of people participate virtually. And a week ago, we were very busy. We made revision. I could say this is second meeting. Before it was consultancy. Revision of milestones documents. These documents was printed in 2012, very old, and nobody tried to touch it because it's very difficult to change the text, but we found it's very reasonable and important, and we sit down together and made a lot of work. We received a lot of proposals. We discussed these proposals, and I hope in nearest 1-2 years we'll produce new documents which will be actual in accordance with nowadays standards and safety requirements of the agency. This is again the picture about milestones, how many people from Africa and examples of African countries who participated in some of this year. Now about capacity building. We have 3 mechanisms of capacity building, like distance training, internet reactor laboratories, basic training like regional research reactor schools, and advanced training. I could say it's the most serious. This is international centers based on research reactors. This scheme is focused on countries which operate in research reactor or newcomers, and as maybe a part of preparations for nuclear program. But again, a lot of times we receive questions from countries: is it obligated to have research reactor if you go in to construct nuclear power plants? No obligations. Moreover, I could say that operation of research reactor is very different. of operation of nuclear power plants, but like educational purposes, it can be very useful. And many countries follow this because it may be the first more or less serious project relative to nuclear technology before construction of nuclear power plant. Second one, first one, sorry, Internet Reactor Laboratory. Idea is that there is the host country and there are guest countries, and host country provide experience from the reactor online to guest countries, and participants from guest countries not only receive lectures and see experiments, but they can receive data and make own calculations. It's very active project of the agency. We have some troubles. A year ago, we had troubles with new internet protocols. And finally, thanks to colleagues Bilal, Chafik, and Pablo, and other colleagues from our hosts, we found solution like cloud solution. And now we don't need to provide some equipment for member states. It's easier to use existing cloud technologies, and it can bring new possibilities for countries. They can be connected to different hosts. We will discuss this later. Yes, please. Good. This is how many countries in Africa participate in the Internet Reactor Laboratory. Yeah. Second one, regional research reactor schools. Nowadays, we provide 3 research reactor schools per year. You see how many participants obtained possibilities of these schools. In fact, it was half of year ago information, more than 100 participants from different countries. And in 22nd, first research reactor school in Russia. You see behind the people icebreaker, which now in North Ocean. Research reactor school in Japan. First, I could say, in fact, it was third, but for our section, it was first research school in Rabat, Morocco, very successful. And again, a lot of participants from Africa. First school in Spanish language in 2023 in Bariloche and Buenos Aires, Argentina, again in Russia. First French school in Grenoble, Saclay, and Cadarache. This year, Morocco, Buenos Aires, and Bariloche, and Osaka, Kyoto, Kendai University, Wakasawan, and Kyoto University. Next year, we'll have 3 schools. Again, 1 school in Russian Federation, second one will be, and I hope it will be new one in Canada, and third one again in France. About ICERs, this is high level, I could say, centers, like centers of competence, and the role of the agency to help to organize and to confirm the qualification level of these centers. And participants usually well-suited professionals or juniors who know what means nuclear and who make own experiments in these centers. Sorry. On this picture, you see how many centers just is installed. In 2025, the last one at the moment, it was Argentina. About human resource development. Okay, I do not have a lot of time, but idea is very simple. One of the question of country, especially newcomer country, how many people in time frame and how many resources necessary to spend for research reactor program. For these purposes, we collected information from different countries, and the model can give you possibility based on your size of reactor, like small, medium, or large, as well potential utilization. You can receive some numbers for your staff, for your operating personnel, for regulatory body, for utilities, and for the rest of research reactor program. You can see some pictures here. We organized two trainings. First one was in Senegal. Second one was in Kenya. And I could say that this activity is very, very requestable. The last one this year, it was in Saudi Arabia. They fight it with us. They asked us to come. We were very busy, but we did it in 3 days. I'm not sure that it was very effective because usually we need to spend 1 week, but it was their decision. And potentially we have a request from Nigeria. I hope it will be much next year. Ethiopia, Rwanda, Uganda, Niger, as well. We had discussions with Vietnam, Bangladesh, Turkey, and Malaysia. It's clear, I think, as I will say about this, a lot of support of TC projects, national, regional, and international. About publications, at the moment, the most important for us specific consideration is Milestones project review of the document. After that, it will be review of technical requirements and feasibility study, and maybe we'll have new documents production for IRL, Research Reactor School, and ICER centers, and HRD modeling guidance for research reactor programs. Thank you very much.
Thank you very much for the wonderful presentation. Are there any questions? One.
Thank you very much. This is a comment, in fact. Thank you, Andre, for a very comprehensive presentation this morning. I just would like to add, as a program management officer for the project, for the regional project for Africa, to support embarking member states to establish their first research reactor program, that we have, for the first time ever, kicked off the project with engaging high-level officers from the 8 embarking countries. We have invited 8 ministers, permanent secretaries, and ambassadors to understand the IAEA milestone approach so that they can go and get high-level government commitment. And without this government commitment, I have seen some of the countries throughout the project lifetime, they withdrew from the project in a way that they were not able to sustain the government commitment. So this is a very important point that I would like here to raise, that without having a high-level government commitment that is sustainable beyond the current government, the project would not flow. Thank you.
Thank you, Aza, for your comments. I just mentioned, as you remember, that I have some pictures and I have slides about this, but due to the lack of the time, it's 20 minutes exactly not enough for this project, because we have a lot of activities and a lot of important issues we should deliver to countries. Thank you.
Any other question? I think you can get more clarity during tea, right? Is that fine? Thank you very much for highlighting the IE activities. Our next speaker is Pablo Cantero. I must not say your name wrong. Did I say it correctly? He's speaking on necessary technical and management capabilities, teamwork, and contract format. Insights from the RA10 reactor project. Over to you, sir.
Okay, can you hear me? Yes, thank you, Mr. Chairman. And good morning to everyone. I will not be the only speaker in this presentation, because as the title of the presentation says, we want to present to this community the challenges of conducting such a project that we are conducting together with INVAP. So I will share the presentation with Fernando Gutierrez here at my side. You see, same positions, project manager, but different companies, the owner and the vendor. And what we want to share with you today is not the status of the project. I will go to present the status of the project and some minor technical descriptions, but this is not the important part. You already know the R18 reactor, but if you have questions, we can go in deep. But what we want to share with you today is the challenging, what a project like this is, and what we need to focus on to be successful in conducting such a project. So at the beginning, we are going to have some views of the project. And one important thing also in this presentation is that nuclear capacity of a country. Argentina is a proven country in the capacity of specifying research reactors, designing research reactors, and constructing research reactors. And this is because we managed to work together in the last 5 decades, National Atomic Energy Commission together with INVAP, building this capacity, training people, teaching, educating people, developing technology, and now we are building a big research reactor in Argentina, and this is, I would not say a conclusion, but it's like an expression of the capacity of the country. So I will include also in this presentation some aspect regarding the capacity of Argentina for building, designing, and commissioning research reactors, and what are the bases of this capacity in the country. Well, this was a long introduction, but it's important to see the frame, the scopus of this presentation. Early in 2007, we started to think about building a new research reactor in Argentina, gathering requirements from the stakeholders in the country, and we came to 4 main objectives: to meet the increase in radioisotope demand in the local frame, but also in regional approach, consolidate in the fuel cycle, specifically fuel elements and nuclear materials, incorporate new neutron techniques with the presence in the reactor of high quality beams, and also the contribution to support, maintain, and increase the nuclear capacity in the country and in the region. So those are the main objectives of the project. And we came to a project of 30 megawatts thermal power, open pool, fuel elements, low enrichment, MTR type, moderated and cooled by light water, but heavy water reflector tank, as is the Argentine technology, 2 diverse and independent shutdown system, and is controlled by 6 half-beam control plates. The design includes 4 buildings, the reactor building, the reactor building, well, it's not so relevant, but you can identify the reactor building, the guides building, and auxiliary building is mostly office and a service building. The total built area will be roughly 1,800 square meters, covered square meters. And this is a brief description of the capabilities of R18. We have a thermal beam for neutron radiography that will complement the capability of irradiation services within the core and outside the core. 2 cold beams that are facing a cold neutron source. 2 positions in core for fast neutron irradiation. This is mostly to support material and research. 4 positions also in core for thermal neutron irradiation. One of those positions is able to allocate a new fuel element for qualification. 7 positions for the pneumatic transfer system, each position with two headers, so in total we have 14 positions. Then we have the radioisotope production services, 10 for moly, 4 for iridium and lutetium, and 3 that is shared with industrial iridium and other radioisotope. That is a facility that we are offering for the researchers to develop new radioisotopes at the reactor. Then we have 5 positions for silicon doping, 2 6 inches, 2 8 inches, and 1 10 inches. And we also include MPP fuel rod testing pressurized loop. This is an innovative solution. This loop will not move in order to be able to have the ramp, the power ramp experiments. We install surrounding the volume under testing a poison chamber, and we manage to increase and decrease the concentration of this neutron poison, and this is the way that we manage to perform the ramp up of experiments for the fuel qualification. And the good thing that is the position is fixed there. And finally, we have two thermal neutron beams. So this is the facilities that are in the reactor. This is the status of the reactor. I will show you in picture. This is the civil construction, already ended. This is a picture from 2 weeks ago, maybe? Yes, 2 weeks ago, the top of the pool. You can see all the internals of the pool on the reactor pool is almost done. Few components still to be installed, and also in the service pools. This is a view of how the installation is going on there. This is the guides building, the back guides hall. This is a view from the cooling towers. You can see these also some tanks on the left and the service building behind. Sorry, another view of that part. One word about fuel elements. That is also important for nuclear capacity in a country. Argentina masters the technology of designing fuel elements. Several facilities related to this. We have designed things in CNEA and also in INVAP. We have a plant, research and developing plant in CNEA. It's called ECRI, that has the capability to build the fuel elements and the prototypes and to feed the process of qualifying new designs of fuel elements. In the case of RA10, it is a new design. It was qualified and it's already manufactured. For the future provision of RA10, we are evaluating to make a technology transfer to Conuar, which is our fuel elements company in Argentina. They are already building the fuel elements for RA3 reactor, and is maybe the option for us also to build to manufacture the fuel elements for RA10. So far, we are manufacturing the fuel elements at ECRI. We already have the startup core in place, and we are starting with the second and the third core for the manufacturing of the second and third core. The status of the project, the total global advance is 85%. One thing that is important that we already delivered the safety report to the regulator for gathering the commissioning license. And the commissioning team is in preparation and is roughly 80% in advance. The total investment so far is $430 million. Some challenges that we have to complete the provision and installation and the pre-commissioning. And the idea is to achieve a complete and consistent integration of all the systems before we start the commissioning, and then after the pre-commissioning test, we are going to start operating the reactor for the commissioning. One important thing that is important to remark is that in Argentina, we also have the capability and the capacity to train the operating staff of the reactor. So we started early in advance in this project with 30 professionals and 20 professionals and 30 technicians. We educated them, we trained them. They are all licensed now, and they are under training for the specific licensing. This is something that is demanding in capacity and in energy to get to the point of commissioning with a consistent operating staff in place. And this is the project timeline. Nowadays, we have already started the pre-commissioning test. We are confident that we are going to be able to finish the pre-commissioning test by August next year, and then we will start the commissioning, expecting the first criticality in December next year and delivering for operation in August 2027. Speaking about capacity, what is Argentina related to the provision of research reactor, but not only in the country, but also abroad with the collaboration or with INVAP as the company providing these facilities. As you can see in the upper line, those are our facilities within the country, and in the bottom line, there are the facilities that we send or sold to the world during the years. And this was made based on the capacity of the country. And one important thing in the capacity of the country to build the capacity is the Balseiro Institute and other institutes that we have in CNEA. I'm focused on Balseiro Institute because it's the oldest one. This is the academic offer of the Balseiro Institute. As you can see, we have 4 undergraduate careers, 3 diplomats, and 9 postgraduate careers. But the good thing here is that we have physics, nuclear engineering, and mechanical engineering as main pillars of the capacity building for nuclear infrastructure in the country. And one way to show you which is the impact of Balseiro Institute, you can see it was established in 1955, and the line, you have 2 lines here. One is the company, and the other are institutions. You can see INVAP was early established in 1976, based on this capacity that we built based on Balseiro Institute. And after that year, we started developing a lot of companies and institutions supporting the nuclear capacity in the country. So now I will share the stage with Fernando.
Thank you, Pablo. As Pablo said, I will talk about something what happens before operation and utilization multipurpose reactors. That happens before is a complex project. Multipurpose reactor is, as you know, Marisa, a complex project. In these kinds of projects, 2 fundamental dimensions always coexist. On one side, we have the technological dimension, the hard skills. And on the other side, the dimension of management, leadership, and coordination, the soft skills. Of course, the distinctive elements that brings us together today is the nuclear aspect, and that is why we are at this conference. But it's important to emphasize something. Nuclear technology does not organize itself and does not manage itself. It requires a solid project management framework that structures, prioritizes, and integrates all that expertise, knowledge, and background. The wide range of required capability make it almost impossible for a single organization to encompass all of them. That is why these projects inevitably become collaborative efforts. In nuclear projects, this collaboration is formalized through contract between organizations, but contracts are not an end in themselves. They must enable things to move forward. They must avoid becoming obstacles, and they must keep expectations aligned among all parties. In this sense, the role of contract manager is crucial. Even when scope is truly analyzed, contract can never include everything. Because of complexity, because of interdependencies, and because of long-term horizon we work with. And this is why relying on penalties as a way to correct the behavior of other parties is unrealistic. What truly matters is establishing clear processes, solid methodologies, and a precise definition of roles and responsibility across organizations. This is where soft skill, teamwork, leadership, and complex project management capabilities come into play. Team composition is essential and perhaps the most critical decision. So is the selection of suppliers and contractors. Many suppliers come from industrial background and they must receive a nuclear coating, which requires two fundamental elements, quality assurance and nuclear safety culture. To this, we must add the large number of suppliers and subcontractors involved. Multipurpose reactor projects tend to be built on long-term relationship, on trust-based contracts, and on sustained collaboration. At the end of the day, everything comes down to finding a balance between technology and management, between technical capabilities and planning, between objectives and constraints. And I want to insist on something. This is not only about the contract. It's about how well organizations know each other, how well they can work together, and how much trust they have been able to build. In short, it's about our capacity to work as a team. Reaching the stage of Pablo mentioned is in fact proof that we have been capable of doing exactly that. The challenge now is to continue along the same path till the end, and this will be the challenge for all future multipurpose reactor projects. Thank you.
Just thank you, Fernando, and I completely agree on everything that you said. And this is why we are here together, to offer our experience that we need to build trust, we need to build a focus, the same focus, and be aligned in the objective. We are now being very stressed every day, I would say, from different issues, different problems. You know that Maximum says that at the end of the project, the most quantity of problem appears, and this is the real case now. But we are confident that working together, close together, discussing what the problems are and the solutions that we agree is the only way that we have to be consistent with the schedule that we have now. We are sure that we are going to succeed. We are working for that. And this is why we wanted to share with you that these challenges are from the beginning, but they appear at the end of the project. So as final remarks, I would like to say that R18 projects illustrate the ability of Argentina not only to build, to conceive a research reactor based on the requirements of the users and the stakeholders, put those requirements into requirements for the project, design, build and construct and commission, license and train the team. So the whole environment related to a research reactor provision is mastered by Argentina. And this has not been possible in Argentina only with the CNEA, neither only with INVAP. We work together, and our capacity stands on this collaboration for last 5 decades. And we support each other. Even though in this project we are client and vendor and we fight a lot, as a country we support each other. They support us operating our fleet of reactor, and we support INVAP in training and some technological developments and some analysis. So this is the relevant thing that we want to live here on this stage. Collaboration, long-term work together, trust the organizations, and this build capacity for nuclear providers as a country. So thank you very much. We are eager to answer your question if you have.
Thank you very much, Pablo. 3 minutes early. 3 minutes early. Okay.
Morning. Thank you for the presentation. Very insightful. I have actually 2 questions, but it will be quick. The first one is the human resources like operators, maintenance people, and also engineers. What is the best time to identify your skills and send them for training?
when you design the reactor and to operate it. Once you have criticality, the vendor will start up the reactor with those people. What is the handover phase? 10 months to 1 year, and the support after that for how long?
Well, you will have a complete presentation on this topic this afternoon, provided by Fabricio. He is our reactor manager at RA6, but he's also leading the training of our team in RA10. But coming back to the time frame, we started 6 years ago with our team. This is not because it was needed to start 6 years ago. It was because the project delayed. But anyway, I would say that given our requirements of training, education, training, and the licensing process, at least 2 years in our case, for training the people. Also, establishing the programs was something that is time-consuming, and our operators are also working on that. They are conducted by experts, but they are working on the development of the plants, and this is part of the training for them. And we're going to start the commissioning process with our team and the support of senior operators from other facilities in Argentina, and they will support our new team in the process of commissioning. After that, our expectation is that the operation of everything will rely on the new staff. And the maintenance, as far as we have the programs, we have some specific activities, processes that will be inside in-house, and others that we're going to bring from outside, from providers.
All right. Any?
Thank you very much for that beautiful presentation. Yesterday we were trying to extract from the vendors how much it will cost a research reactor for the construction of a research reactor. We didn't get any favorable answers. The only answer we got was that it's going to be cheaper than any other company, but that's not a good answer. But today, luckily, you did say that it will be, you have spent about $420 million US so far. So can you please just complete it so that people who are intending to purchase research reactor will get information from you? Thank you very much.
Maybe we can give you two type of answers. One is from my side, that is the client, and why the problems that we have, and why the budget is the budget it is now. And maybe from the vendor you can say some different words, it's up to you. But we spend Argentine pesos. We do not spend dollars. Yeah. And when we started, the value of the Argentine pesos was 4 to 1. 4 pesos, $1. Yeah. Now is 1,500 pesos, $1 US. So the devaluation of the money is very important. And this happens inside 1 year, you know? So your original, and our budget is yearly basis. Mm. So we started in 2010 with the design. We are almost 15 years of project. This is not the real time for a project like this one, but we have some economic restrictions during the process. And once you start the building, the reactor, if you don't have the budget that you need for the year, that limited budget has less impact on the real advance of the project, because you need to maintain the infrastructure of building such a capacity reactor, but you are not having money to pay for the components. So it's difficult to say the real number based on this reactor. What I can say is that I expect that we will finish this project with a budget of $500 million for the complete reactor, from the design to commissioning. But if we could manage to do this work in the expected timing at the beginning, the budget would have been less, for sure. How much less? Difficult to say. 20%, I would say maybe yes. Maybe yes. but not in 15 years, in 7 years. Yeah. I don't know if you want to add something about budgeting and pricing.
The amount of money is information of our client. For R18 is information that Paulo said.
Because you were on time, I'll take one last question. Is there...
Sami, here.
Sami.
Yeah, thanks, Pablo, for that wonderful presentation. I think in one of your slides towards the end, you indicated the licensing process. It's an Achilles heel for most new projects. Do you want to comment, because you've got experience in, as INVEP, in installing these reactors? What was the licensing process like in terms of budget as well as schedule? Thank you.
Sure, Sami. I didn't want to include that here because it's a big bunch of information, but two things. You said the process itself and the budget related. Please realize that our safety team is within the CNEA, so we didn't pay for them. So the budget that we spend on licensing, it's some tricky in our case. But the process, it's important that you keep in mind that safety analysis is not licensing. Many organizations think that safety analysis is and make the safety report and we are done. And this is not the case. Licensing is a complete process dedicated to show to the regulator that you are building a safe machine within the requirements of the regulator. Safety analysis is one part of the licensing processes. Then you have to deal with the regulator, you have to show them, you have to write the safety report in the way that they are expecting that you demonstrate that you are fulfilling the requirements. So in our case, we put a licensing team, an entire department within the project to manage the licensing process, and we have a safety, nuclear safety and radiological safety team with much more people than the licensing process within CNEA supporting the licensing process of R18. So in total, we have working for the licensing processes roughly 40 persons, 6 within the project and 35 in the supporting organization from CNEA. And one thing that also is important is the relation that we had with the regulator. We started to manage the regulator early in advance, making monthly meetings with them, telling them what we are going to do with the reactor, asking them if they have some needs to be sure that we are going to fulfill all their requirements. And in any case that we have any requirement from them, we make a big effort to offer all the information. When we made a change in the design after the construction licensing, we make a meeting in advance. We show them which is the change. We discuss, and once they agreed, we will go forward with the change. So 3 things I would say. Keep in mind, licensing is a whole process itself. 2, manage the expectation and the anxiety of your regulator. In the good, I say it in a good way. You need to be partners with your regulator in order that the process go forward. And the third part, try to find a safety analysis team to support your licensing process. And the budget for us was not too much because we have the people inside the National Atomic Energy Commission. You're welcome.
Thank you, Pablo. There's a few more questions for you, so you will talk during tea. Make yourself available. There's a few more questions.
Just one more comment. Andre told me, in our case, our regulator also have a fee for giving the licensing. Yeah, it's important also that you have to keep in mind. I don't have the numbers now, but I will get the numbers and we can also share with you.
So our next speaker is Marisa van der Walt. Marisa, this is a very common last name in South Africa. We must take you for ourselves, right? You can come help us build the MPR. Lessons learned from the Pallas reactor under development in the Netherlands. Up to you, man.
So in actual fact, I am South African, and I left South Africa 11 years ago. I worked at Pebble Bay Modular Reactor and at Nexa, and then I went to the Pallas reactor project. So thank you for allowing me to share the lessons learned of the past very difficult, hard 11 years, but very good 11 years of the Pallas reactor project. Oh, I need a thing. So the Pallas reactor is one of the most important projects at this time in the Netherlands, and not because of the need it alone, but also the fact that we are, like a lot of you, anticipating 3 to 4 new bolts in the Netherlands. So our aim is to produce radioisotopes and also to support in a niche market the nuclear industry. And for this, we have complete support from the Dutch government. We worked very hard as a project team. We went through many due diligence, many questions to get the support and the trust of the government, and we at this stage are fully funded by them. And we are funded by the Ministry of Health, and the challenge continues because the governance that is required, the amount of responsibility that we have towards our stakeholders are high. We also make use of the infrastructure that is already there, as we are replacing the HFI reactor. And you can see there in the screen the location. It's close to the sea, and it's in the North Holland. And we have good ties with our customers, Curium, and so forth, and we are well established in the nuclear industry. As a project, we have overcome many challenges, and we've reached many milestones. As I said, one important milestone was the funding that we've received, but also, as you know, it's very challenging to get a nuclear license in Europe, and we were able to get a nuclear license, a license to construct, and we also formed a team. I was number 7 on the project, and we've grown this team to more than 200 people. We have also signed contracts with ICOS, and ICOS is a consortium of INVAP. And we have a year or 2 ago signed a contract with FCC, and FCC is a Spanish constructor, and together in a joint delivery organization, Pallas, ICOS, consisting of INVAP, and FCC will build this reactor. So as I said, it was a long journey up to now, with a lot of hurdles that we overcame. We started with a tendering process in 2017, 2018, when we signed the contract. We have delivered the concept and basic design, and we are currently in the tail end of detailed design. We have also started some construction activities that I will share with you at the end of the slide. As I said, we work in a joint delivery organization, but for the design, our delivery strategy is we started off with a set of user requirements where we specified in a functional way what we want as a design. We also have a set of project requirements describing how we expect the design to be developed and what we expect from our contractors. These are important measures because, as my colleague said, the soft skills are also important. So communication is key within a project, and having project requirements and user requirements that are well defined helps in communication and delivering a reactor that the customer wants. We also follow, and I will explain to you, a V model, where we constantly verify and validate throughout the process that we are getting the right design that fits our needs. We follow an engineering, procurement, and construction management contracting model, and this enables collaboration because you don't buy a design, you procure designing resources, and it also brings challenges in terms of delivering, in terms of on time and budget, so you need to be creative to steer your project in this way. We have done a lot of work with ICOS INVAP, and we have a beautiful design. It's a 25 megawatt reactor, but it has the capability to be ramped up to 30 megawatts. It's an open pool type reactor, and it's heavy water and moderated, reflector vessel of heavy water. And you can also see that there's a cutout piece in the reflector vessel. And this allows for flexibility. Flexibility is key when you design a reactor because you do not know how the world will look in 10 years, or 5 years, or within 20 years. We followed strictly and with a lot of collaboration and with a lot of discussions an integrated design approach to make sure that our needs are adhered to. And we have very special safety features. So INVAP brought to us a very safe reactor in terms of fulfilling the Dutch safety requirements in protecting the reactor against external internal flooding. We also have an aircraft crash protection shell, and our design is designed against extreme weather conditions. We have passive systems, we have increased redundancy compared to previous designs, and one important feature that we have in this reactor is that we can shut down the reactor in a diverse way, and this was a strong driver from the licensing requirements. And the design that we have is also very good in terms of reducing the dose to the worker, especially around the pool area, as the heavy water, the warm water layer helps the workers to have less dose when they operate the reactor. So the requirements definition is a very important stage, as I said. It enables further on an integrated design, and it helps in the discussion, and it helps to define and realize a reactor where the requirements are implemented in a balanced way. So we have a business case, and there was a lot of iteration at the beginning between the business case and the design to be able to realize something that is best for project and best for market. It is the first time in 60 years that our regulator, the INVS, is licensing and overseeing a new reactor in the Netherlands. They are not a prescriptive regulator, but a goal-oriented regulator. So we had to take the regulations that they had, grade it for our reactor, because we started off with power plant type requirements. That was a big challenge, but also very productive in terms of taking our regulator along into the design. It is key that your regulator understands your design. The more they understand your design, the more trust they have, and the more they support in the licensing process. Also, it is important and to take and have the necessary security requirements in place. And as I said, I cannot emphasize more, have these requirements implemented in a balanced way so that you can achieve your goals. And that's why it's important to look and make choices based on value, what brings the value to you as the customer. And what we did is we chose a reactor with a power as low as possible that enables our business case, but also enables a licensability. And we drive and have a lot of discussions and work with INVAP, ICOS, on producing a reliable and available reactor, and also something that is flexible and adaptable for the future, because that's very difficult to quantify. And as I say, we don't have what's the word? A magic ball or to be able to forecast the future. So you need to really think about how do you implement flexibility, adaptability, and simple operations. Simple operations also means that people can step in and ensure the availability and reliability of the reactor. This all forms part of an ecosystem, a complex ecosystem. And it's an n-dimensional problem, so if you have one part can influence many things, so you really as a client need to be able to understand the complexities and oversee the complexities. And for that reason, we've implemented design control measures, and this is for us the foundation of nuclear safety licensing and governance of the design. And we use systems engineering, and I've been working quite hard with my colleague here, Emmanuel, on implementation of systems engineering, making sure that we do requirements management, be able to do the verification, validation, planning, and also the verification and validation of the design. And then there's questions about how much does a reactor cost? It depends on your needs. It depends on the context of your country. It depends on what the regulator expects from you. But what is important is not just how much it costs, but how do you control those costs? And configuration management and systems engineering can help countries to have an overview of your design and how it impacts cost. It is important to have a good definition of your project at the beginning. As I said, you will grow as the design grows. You will learn what you need as the design develops. And there should be in your project the opportunity to grow along with the design. So put effort, put emphasis at the beginning phases from the requirements in the design to have a good definition of your project, because if you do not have a good definition of your project at the beginning, it can lead to poor execution. We are, as the nuclear industry, we can see many examples of reactors that are behind schedule or overrunning on cost or big changes, and putting more effort at the beginning with a good definition lowers the risk in your project in the future. And for that, we have now worked with ICOS, and we have a very good basis for our V to be able to start execution to ensure that our needs will be realized during execution. To do that, one needs suitably experienced people in your team, and this team grows over time. At this stage, we are around 42 to 50 people in the PALAS organization, only focusing and ensuring the design authorship. We are embedded in the intelligent customer. We specified the requirements at the beginning, so we understand the needs, we review the design, we accept the design, and we are responsible for configuration management of the design. What is important is not just the amount of documents that is delivered, but also the quality of the documents that's being delivered, because it is not just, in our case, us that needs to be convinced, it's also the regulator, it's also third parties, and that they are appointing to review the design. So think about that when you start designing and developing processes and procedures. So the lessons learned in terms of design control for us is that systems engineering, configuration management done in the right way provides a basis for trust for the regulator and the financiers. It is a way to elicit requirements from stakeholders to ensure the right design. And stakeholders, I mean people from safety, security, the business case, operations, maintenance, and decommissioning. It ensures a structured way of working, and as it's done right, you can reduce the reworks and you can control cost. As reworks during design and construction is costly, design is not cheap. And for that reason, this is really important to consider in the right way. Also, we have model-based engineering, so we do a lot with 3D models, starting and enabling 3D modeling just to have, as a client, the view of what the designers are developing gives you much more of a sense and control over the design, and it gives you a way to ensure that you are getting what you want. It also helps with training, it also helps with speaking to stakeholders. And depending on the contracting strategy, you need to think about the way of how you are going to manage, oversee, and supervise the design to enable the best interest for all of the project. So this is a little bit of an old picture, but it gives you a view of where we are at this time. We have constructed the Putton foundation of the nuclear island, and we're also busy with the secondary cooling pipeline with FCC. This was a project that was done with BASIX, and there was very good collaboration between ICOS, INVAP, BASIX, and Pallas to be able to make this a success. This looks very small, but it is maybe as big as a football soccer stadium or field, so that gives you more perspective. You can see that it is a very small site. So in the Netherlands, space is a luxury, and it will become more full in the future. So this is something that the teams are working on, ensuring that we have good construction methods. As my Argentinian colleague said, that this is done in collaboration. It is not just the processes, the procedures, it is the soft skills, the way you communicate, the way you interact and understand each other, and only together you can make the reactor and the project a success. So I have one small video, I hope I still have time, to showcase the beautiful work that we are doing. If someone can press the button, because I don't know if I can.
At NRG Pallas, we advance nuclear innovations and together discover how this can support life for good. Specializing in nuclear technology.
So this is like a project, you need to have a lot of patience.
NRG Palace, we advance nuclear innovations and together discover how this can support life for good. Specializing in nuclear technology, we develop and supply medical isotopes and contribute to energy solutions. Coming from various backgrounds and with a wide range of skills, we want to create a future that will benefit everyone. Together, we're building a broader, more innovative medical isotope landscape. We're helping more than 30,000 people every day in the detection and treatment of cancer and other health challenges. We are proud to be writing a next chapter in our quest for a better future. We build the Pallas Reactor.
Thank you.
Look at that, right on time. Do we have any questions? 1, 2, 3, 4. 5. 4.
Okay, thank you, Marisa, for this very thoughtful and very interesting presentation. I am very happy to hear that the emphasis you put in the design phase and the preliminary phase of the project, I think is very important to avoid extra cost and rework. That sometimes the design phase is minimized, or say they want to go very quickly to the construction phase, but there is a process to build the idea, no? to get the idea. So, but I want to refer to some specific thing that you mentioned during your presentation about the design of the power of the reactor is 25 megawatts, but you have the allowance to increase 5 megawatts more. And this is not very common in design of research reactor. There are a few examples in Jordan, for instance, is similar, but I think that the criteria for getting this allowance can be different in your case. So can you explain a little bit why this allowance was taken and what are the justification of this, and what do you need to increase the power in 5 megawatts in case you need?
So this was my lesson learned from Safari reactor, because what we did in Safari reactor is one stage we upped the power to be able to operate at a higher power, and that was due to market changes or needs changes. And as I said at the beginning, you cannot predict the future, but you need to be flexible and you need to be able and adaptable to foresee future changes. We also try to keep the power as low as possible to make the licensing easier, because licensing in Europe is complex and people are perhaps more risk averse. So it was a consideration between licensing, flexibility for the future, and also cost. And what we did is we specified requirements in terms of the primary flow to be able to size such that if we ramp up in the future that will be able to do. And also what I learned from Safari is to be able to have your electrical system designed such that you can also up ramp in the future. Yeah. So 2 simple requirements to be able to have this was implemented. Yeah.
Okay, Marisa, good presentation and quite eye-opening. You started project officially in 2013, and it's 2025 now.
Yes.
So which phase of the project did you spend more time on, and what are sort of the lessons that you think we should take from your experience?
So the Pallas reactor went through, this is not the first bit that we went through. The first, they had a concept of 80 megawatt to 100 megawatt reactor, and the government did not support that reactor to be financed. Then we started again. And we started with the lower power reactors, you saw, really taking account business case, really taking account cost. The most time that we've spent is this time, because from 2014 up to now, because it took time, as I said, to convince our government to give us money. First, we were supposed to get public financing. We saw that there were a lot of stakeholders that were interested, but they all asked, please get a license first, because they want to lower their risk as well. So it took time to get the design such a way that it fits our needs. It took time to get the license, and it took time to get the public financing. Not public, sorry, the financing from the government. Yeah. And this is the important time, like Ruben said. It's if you have a good definition now, then construction goes very fast. If what I've seen, for instance, with the Python Foundation, they can construct faster than what we can design. So you need to be able to be ready once construction starts, because when the machines are standing outside, it costs money. Mm-hmm.
Can you stand when you ask your questions for the camera?
Thank you very much, Marisa. That was a very good presentation. Just a quick one. You mentioned in the design the use of heavy water. It tends to ramp up the capex and the opex at times. Is there any alternative towards the use of heavy water that you have considered in your design? Thank you.
It's like Safari reactor or the HFR reactor, you can use beryllium. What I like about heavy water is that it gives a very nice flux profile, especially when you do beam ports, or if you want to have, like us, out-of-core irradiations. It gives a very good quality product. But at the end, it is your preference, so it's what you want. I think both are good choices. What makes heavy water, this design, as I said, particularly good, is because it gives you a way to shut down the reactor in a diverse way. And if I look at the regulatory requirements and look at what the changes in the future, it is very important to be able to show that you can shut down your reactor. So that was really for us one of the drivers for choosing this. Yeah.
One question, please. Thank you for your good presentation. I have one question. The presentation mentions keeping reactor power as low as possible. We're still supporting the business case. And how was optimal power level determined? Thank you.
What we did is we specified in our technical requirements the products and the specific activity required. And what INWEB ICOS did is they translated that into a flux level. We also gave a minimum flux level that we wanted. So together with using value engineering principles, together with discussing with and working with INWEB ICOS, we came to a level of power of the reactor that suits our needs. Yeah. So you need to have a business case team to be able to foresee what does the market want. So what is a good quality product that the market will buy, and based on that, you can work with your designers to give you a power or flux that enables your business case.
All right, thank you very much. Our next speaker is So those who had more questions during tea, okay. Our next speaker is Mr. Emmanuel Ray, speaking on the use of systems engineering as a tool for design management in research reactors.
Good morning, ladies and gentlemen. My name is Emmanuel Ray. I work at INVAP, and I will present for you today the use of systems engineering as a tool for design management in research reactors. This is work along with Clarissa Mocchiaro, also from INVAP, and Marisa van der Walt, who was presenting a moment ago. The content of this presentation has an introduction about the PALAS project that I will skip because it was already given by Marisa. It deals also with the translation from stakeholder needs into requirements, the requirements management, the verification and validation process, and conclusions. The aim of this work is to summarize the experience gained in the framework of the PALAS reactor project and their development in the Netherlands. The use of systems engineering in the design management of a nuclear reactor allows for the systematic and structured handling of the stakeholder needs from the different are involved in such a complex endeavor. At the very beginning, it is necessary to interact with the stakeholders in order to gather their needs in terms of functionality and performance, also their expectations about the project, its execution, and the results. The stakeholders of the project are knowledgeable in a wide range of areas, turning this task a multidisciplinary work. They provide their needs, which constitute a valuable input for the development of the project. At a great extent, the success of the project depends on the satisfaction of those needs. The completeness of the inputs at the beginning of the project is an aspect to be considered. Not always all the information is available at the very beginning, or not always it is fully comprehensive because of different reasons. It can be because it is directly not available, or just partial, or because a stakeholder has not been identified, or because the stakeholder does not exist yet. Because of all those factors at the very beginning of the project, it is a high impact work to perform an analysis on the inputs in order to be able to produce a complete and homogeneous set of requirements with a consistent approach in order to have harmony in all the design aspects of the reactor. In this regard, it is worth to note the importance of a balance in the definition of the requirement set. The requirement set has to be as complete as possible in order to record and to manage the stakeholder needs, and at the same time it has to be lean in order to maximize the efficiency in the use of the resources of the organization. The definition of a requirement allows for the demonstration that a stakeholder need has been taken into account. The higher the amount of requirements that we define, the higher the degree of control that we have, and also higher the effort that we have to spend on that, the resources that we have to allocate, the schedule, and finally, cost. Therefore, the benefits of the definition of a requirement have to be commensurate with the resources that are allocated to that task. Moreover, it is advisable that during the definition of the requirements, some quality criteria are applied. A set of quality criteria that has shown good results for us is the one known by the acronym SMART, standing for specific, measurable, achievable, relevant, and time-bounded. This set of requirements ensure that the set of requirements are well-defined, aligned with the stakeholder needs, that are realistic, and in the time frame of the project. Following, it is necessary to allocate the requirements to the systems and disciplines, and to that we use the evidence generation criterion. It means that we allocate the requirements to those systems that are able to produce the evidence of compliance with the requirement. This criterion prevents confusion and conflicts at the moment of verification and validation. Subsequently, it is also necessary to allocate the requirements to the different stages of the project. This is aligned also with the criterion of time bounding that we mentioned before, and at the same time allows for a better organization and control of the project. In addition, an interesting exercise to be performed during the definition of the requirements and their allocation to systems, disciplines, and stages is to think of the evidence of compliance that we will be expecting in each stage. This exercise allows for a consistency check about the requirement set that is defined, and at the same time start with the ownership building among the requirements owner for the verification and validation of the requirement. The early identification of the stakeholder needs allow to take them into account in the requirement set and start also building involvement and engagement of every stakeholder in the project. The requirement management is made maintaining traceability between the stakeholder needs and the requirements that are defined out of them. This traceability ensures the integrity of the requirement set, while at the same time contributes to the alignment with the stakeholder needs and to the demonstration that the final results are consistent with those stakeholder needs. Besides, the requirements management has to be defined taking into account to simplify and facilitate the engineering tasks. And also the task of every stakeholder involved in the requirements management process. Every time that we put in front of the stakeholders a process that solves their routine in the day-by-day work, they will adopt that process and they will follow it because it is useful for them. In this regard, it is worth to consider and plan which are the engineering activities that has to be performed by the different disciplines, which are the tools that these disciplines will use to accomplish those tasks, which is the degree of compatibility and interaction that those tools have to present, which are the deliverables that we will obtain from these activities, and how they will provide evidence of compliance with the requirements. Furthermore, we define the requirements, but sometimes it is necessary to modify them. So in order to do that, it is necessary to have a change management process in place. This process has to be defined with an equilibrium between change control and also flexibility for change. On the one hand, it is necessary to have a process in order to propose, assess, approve, and execute modifications in the requirements, while at the same time the impact in cost, schedule, and risk is assessed in order to avoid overruns. On the other hand, it is also necessary that this change management process is flexible and agile in order that every stakeholder involved in the process adopt, carry on, and respect the process. At this point, the importance of systems engineering for the project management becomes evident, providing elements in order to ensure that the scope is achieved within schedule and within cost, and not only during engineering, but also in the rest of the phases of the project. When speaking about systems engineering, we have to have clear in mind that this is an integrative approach with interdisciplinary focus, coping with the complexity of a nuclear reactor project. This holistic view, applied to the satisfaction of the stakeholder needs, has to be embedded in the day-by-day work during engineering, procurement, manufacturing, construction, installation, testing, and commissioning of the reactor. After understanding and acknowledgement of the former ideas, it is revealed as evident that verification and validation of the compliance with the requirements is not just a final step in a process, but is a process that is carried out throughout the entire project, gathering the evidence of compliance with the requirements. It is the result of a deliberate work throughout the entire project. During every stage, objective evidence of compliance is gathered under the form of engineering documents, analysis, calculations, the result of inspections, testing. The responsible people for the requirements of each system gather information that keeps the traceability between the stakeholder needs, the requirements, and the evidence of compliance that is gathered. Moreover, evidence of compliance is also provided at reactor level for those requirements that cannot be verified and validated only by the systems, because they involved either multiple systems or the interaction of some disciplines. At the end of each stage, it is issued a baseline with the evidence of compliance gathered throughout the stage, proving not only that the requirement and its parts comply with the requirements and the specification, but also that it meets the stakeholder needs. The previous slides summarized the experience in the application of systems engineering in the framework of the Palace reactor in the Netherlands. we have seen the complete life cycle of the requirements from the gathering of needs between the stakeholders, the transformation of those needs into requirements, the application of quality criteria for the definition of the requirements, the allocation of those requirements to systems, disciplines, and stages, the traceability between the needs, the requirements, and the evidence of compliance that is provided, the change management process, as well as the verification and validation of the requirements. It has been the intention of this work not only to show the process, but also to show some aspects that enhance the final results that can be obtained, such as, for example, harmonizing the stakeholder needs, the involvement and engagement of the stakeholders, and the ownership building among the responsibles of the verification and validation of the requirements. Furthermore, practical aspects have been shared also, such as balancing the design control with the resources allocated to that, the simplification of the engineering tasks, and the equilibrium between change control and flexibility for change. Finally, it has been highlighted the interdisciplinary and integrative nature of systems engineering, which has to be embedded in the engineering work, aiming at the satisfaction of the stakeholder needs. Thank you very much.
Thank you. Any questions for Emmanuel? 3 questions, right?
Good morning. Nice presentation, by the way. My question is related to the user requirement specification. So when you did your user requirement specification, especially for the core components, am I audible? Can you hear me? Okay, thanks. So on your user requirement specification, especially for the main components like your core reactor vessel, did you specify the design life for those components? Okay, well, the reason I'm asking this question, well, obviously I'm sure everyone is aware that the Safari at the moment is designed to run until 2030, of which we are also embarking on the project to extend the design life because it wasn't properly documented. So I believe if maybe you specify that during the early stages, you'll actually save a lot of money to ensure that, because I believe everyone here that works at Safari still believe that we can still do additional 20 years with additional to the 60 that we just got this year. So did you specify the design life? Thanks.
Between the needs that we received from our client, the lifetime of the reactor was one of them. So there are requirements on the lifetime of the reactor. I cannot disclose the particular data, but there are requirements, yes.
Well, good morning. I just want to find out what were the, yes, I just want to find out what were the challenges that you faced during the initial stages of requirements definition in the project. And number 2 is, how far along did you use the model-based systems engineering in the specific project? Thank you.
Sorry, could you repeat the second question?
I just want to know how far did you use model-based systems engineering in the project?
Well, if I have to say which is the biggest challenge in applying this methodology, is human interaction, I think. That's why I tried to incorporate in the presentation some of these aspects that are not commonly talked or written within the literature, but at the end are the biggest challenges that we face to reach an understanding with the people that we are talking to understand what they need and to agree which will be the final requirement that will be pursued, I think is one of the biggest challenges that we have. The ownership building about the scope that every part has is also a challenge, and the involvement and engagement, as you see, in every case, human abilities are the biggest challenge that we faced. And regarding how long we are using this, we have to say that we are a young organization in the application of systems engineering, at least in the nuclear area. Maybe the space area of INVAP have a little bit more experience on that, but let's say 5 or 7 years.
Hello. Thank you very much. I'm Koos Duberein. Yes. From my side, on the system engineering processes, you put a lot of emphasis on the stakeholder requirements as well as compliance to all the requirements. As part of your processes, do you also perform supplier qualification? Of course, INVAP is a supplier. He should be a qualified supplier because of safety systems 1 and 2 they will install. But also the subsidiaries in the project, all of them must be qualified suppliers. Do you have experience in that, and do you perform supplier qualifications?
Yes, the supplier's qualification is part of the quality system that we followed. So in this sense, we have a higher experience in that because it was also implemented many years ago. In the framework of systems engineering, we are applying this methodology not only in INVAP, but also in some subcontractors that we hired for some specific engineering activities. The standards are the same throughout the entire project.
Thank you, Emmanuel. A round of applause for him, please. The next speaker is Mr. Feng Shi. He's going to speak on the research progress of high-temperature gas-cooled reactors in China and key technologies for aging management consideration.
Okay, thank you. Good morning, everyone. My name is Feng Xie from Institute of Nuclear and New Energy Technology, Tsinghua University, Beijing, China. I'm very glad to have a chance to introduce our research work. My presentation title is Research Progress of High-Temperature Gas-Cooled Reactors in China and the Key Technologies for Aging Management Consideration. This is the outline. First, I would like to spend a little time to introduce our institute. Then I will introduce the research background and the significance, including the research progress of high-temperature gas-cooled reactors in China. The third part will reveal the practical experience in aging management, including domestic and international reference systems. The fourth part will detail how we built an aging management system for HTGRs. Finally, we will summarize the key findings and outline future research directions. And the ANAT of Tsinghua University was founded in 1960 as a top nuclear research and experiment base in China. It has developed into a comprehensive research center with multidisciplinary research, design, and engineering projects, mainly on nuclear technology. 3 nuclear reactors have been built to facilitate research at ANAT, which are the twin-core experimental shading reactor, a 5 megawatt nuclear heating reactor, and a 10 megawatt high-temperature gas-cooled experimental reactor. The ANAT has 2 sites on and off the main campus of Tsinghua University. The main research base of ANAT is in the northwest of Beijing, about 40 kilometers away from the main campus. ANAT has about 400 faculty members, over 200 graduate students, and 17 research divisions. And then I will introduce the research background and the significance. Nuclear power is a green baseload energy source that replaces fossil fuels. And the Generation Force International Forum indicates the technology roadmaps in 2002 and 2014, defining 6 reactor types, including the solid cooled fast reactor, lead cooled fast reactor, gas cooled fast reactor, the high and very high temperature reactor, a supercritical water cooled reactor, and the molten salt reactor. So the Generation Force reactors stand out for their enhanced safety, economic competitiveness, less nuclear waste, and effective prevention of nuclear proliferation. And in China, the research and the development of high-temperature gas-cooled reactor is led by the ANAT Tsinghua University. After more than 5 decades efforts, we have made a series of scientific research advancements. We carried out the basic research in the 1970s. We started to design the 10 megawatt high-temperature gas-cooled reactor from 1986 and achieved its full power operation in 2003. Then based on the research experiments of ETH-10 and also the AVR from Germany, the HTRPM, the world's first pebble bed modular type high-temperature gas-cooled reactor demonstration nuclear power plant, started to design in 2001 and entered its commercial operation in December 2023. Currently, more larger nuclear power plant with 6 modules, the HTRPM 600 is under construction. Compared with pressurized water reactors, the ATGRs have inherent safety and high temperature features. For inherent safety, it means even in most severe accidents, the silicon carbide layer in triso-coated particles can remain intact and return most fission products, preventing core meltdown and large release of radioactivity. Since the high temperature of helium output, the ATGRs have a broad prospects in the process heat application and nuclear hydrogen production. This picture shows the spherical fuel elements with a diameter of 60 millimeters, while in the fuel elements there are thousands of triso-coated particles with a diameter of 1 millimeter. And a brief introduction of the HTR-10, which is the first ATGR in China. It was constructed in 1995 and reached its first criticality in 2000. Many important achievements have been made upon the ATR-10, such as the inherent safety demonstration test. These pictures show the structure of the reactor core and the steam generator, reactor building, main control room, and the graphite reflectors in the core. This table presents the main parameters of ATR-10. In addition, the graphite reflector in ATR-10 is about 60 turns, and the carbon insulation layer is about 42 turns. Based on the ATR-10 and the ATR-PM, we have carried out research on reactor radiation safety. This is the research framework and the representative achievements. We have finished several research projects, nuclear chemical states and the reaction prediction in advanced nuclear energy system, tritium source terms and behaviors in ATGRs, and inherent safety quantification and evaluation for pepper bed reactors. If you are interested in one of these topics, welcome to contact me for future cooperation. And today I will focus on aging management for the HTGRs. As HTGR technology advance, aging management becomes critical. Its value lies in both safety and economy. For the safety, aging management can prevent critical issues like graphite cracking and fuel leakage, ensuring the integrity of the reactor safety. For the economy, HTGRs have high construction and decommissioning costs. Effective aging management can extend their service life from 40 years to over 60 years, avoiding billions of yuan in cost of early replacement and reducing economic losses from power outage caused by aging-related failures. Thus, building an HTGR aging management system is vital for enhancing nuclear safety and economic benefits. And despite its importance, HTGR aging management faces three core challenges. Inadequate mechanism research, like graphite and carbon-based components are core materials for HTGRs. However, their aging mechanisms remain unclear. Lack of data accumulation. There is no standardized process for collecting aging data, such as the fuel element wear rates or graphite deformation. Incompatible system. Measure aging measurement methods for PWRs cannot be directly applied to HTGRs due to their design differences. These gaps means that an HTGR-specific aging management system has not been fully established. So it's urgent for us to perform the research on aging management technology for HTGRs. And to address these challenges, we developed a systematic research framework, starting with HTGR development background and aging management issues, summarizing domestic and foreign aging experience, building a tailored aging management system, and finally proposing conclusions and future directions. This is our research framework diagram. And next, we will introduce the domestic and foreign experience in aging management for reactors, which is an important foundation for building the HTGR aging management system. And as we know that for the aging management, it is a life cycle engineering activity that identifies, monitors, evaluates, controls, and mitigates performance degradation of structure, system, and components caused by environmental factors like high temperature, corrosion, radiation, mechanical loads, and time. Its main stage includes defining evaluation scope and screening aging management objects, conducting aging management reviews, reviewing the effectiveness of aging management programs, and performing time-limited aging analysis. We also extract 5 core review principles based on the HR10's review report. And by December 2023, China has about 18 in-service civil research reactors. However, 3/4 have operated for over 30 years. The high-flux engineering test reactor and the pore-type light water reactor have run for over 40 years. Their OLE practice provide valuable lessons for HTGR aging management. The OLE safety demonstration for nuclear units includes 7 key tasks: defining benchmarks for license renewal safety demonstration, defining evaluation scope and screening AMR objects, screening time-limited aging analysis lists, and conducting demonstrations, building OLE aging management programs and reviewing program effectiveness, conducting OLE environmental impact assessments, and updating the final safety analysis report and implementing safety improvements. And for the international reference, the IEA aging management process provides strong framework guidance. However, the practical operability still need to clarify. the US has a multi-agency collaborative system. This creates a complete aging management loop. Additionally, France revalidate operating licenses through periodically safety reviews. To summarize, domestic OLE practice provides localized process reference, while international systems show diverse management models. And now we move to the first part, establish the aging management system for HTGRs. Our HTGR aging management system is built on 3 pillars: domestic and international nuclear safety regulations, IAEA requirements, and OLE frameworks from domestic research and commercial reactors. It has 5 core evaluation modules: basic screen, defining scope and screen objects, process review, conduct AMRs, program verification, review program effectiveness and lifespan analysis, perform time-limited aging analysis, and special support, conduct key performance experiments. We also compare the similarities and the difference between the aging management system of HTGRs and PWRs. Their main goals align, however, they differ significantly in corrosion and irradiation mechanism. This would lead to need for HTGR-specific design. And using this system, we achieved the preliminary results with the HTR10. First, we screened the AMR objects for mechanical systems. This table lists the key AMR components across 12 core systems, such as reactor pressure vessel belts, steam generator heat transfer tubes, and the in-core graphite components. These are critical for monitoring and evaluating mechanical system aging, such ensuring reactor structure integrity. And second, we analyze the primary loop compartment components. The concrete body acts as a pressure boundary, equipment support, fair flood barrier, and the radiation shade. Support structures ensuring equipment stability. We mapped these components to their function and the AMR objects. And third, we identified AMR priorities for electrical and instrument control system. Cables, cable joints, connectors, and electrical penetrations are core to stable electrical operation. They degrade easily under high temperature and radiation. Now let's compare the aging management technical characteristics of HTGRs and PWRs. They have the same objectives, both focus on nuclear safety, extend the surface life, and improve economy by controlling SSC degradation and reducing accident risks. They have interoperable assessment frameworks. Both include the data monitoring, aging mechanism evaluation, and mitigation interventions. They have similar aging drivers. Both face degradation from operational load fluctuation, environmental medium, and neutron irradiation. However, their corrosion mechanism differ sharply. In HTGRs, the high purity helium was adopted as coolant, operating at 300 to 950 centigrade. Key corrosion types include graphite oxidation, high temperature helium corrosion of metals, and melt field cladding oxidation. Management focus on helium purity control, oxide film formation on graphite, and high temperature metal corrosion monitoring. While in PWRs, the light waters was adopted as coolant, operating at about 300 centigrade and high pressure in an aqueous chemical environment. Key corrosion types including electrochemical corrosion, corrosion fatigue, and secondary corrosion from radioactive deposits. Management relies on water chemistry control, corrosion inhibitor, and regular non-destructive testing. This difference stems from coolant and operating conditions. And the irradiation damage mechanism also differs a lot. In HTGRs, irradiation environment is characterized by fast neutrons and high temperatures. Key damages include the graphite lattice dimension changes, metal creep induced strength loss, and the irradiation induced the cracking of silicon carbide layer in triso-coated particles. Management involves annealing irradiated graphite and monitoring field element irradiation performance, while in PWRs, primary coolant uses high temperature, high pressure borated water as coolant. Key damage includes reactor pressure vessel, brittle fracture, stainless steel thermal embrittlement, and metal fatigue. Management focus on pressure vessel defect detection and in-service inspection of components. This difference requires ATGR aging management to prioritize graphite and triso-coated particle field irradiation damage control. Finally, let's summarize our findings and share future perspectives. Based on our research, we can see that aging management effectively controls the impact of fatigue, corrosion, and radiation embrittlement, reducing nuclear safety risks and meeting regulatory requirements. However, research on ATGR-specific aging mechanism remains insufficient. By analyzing aging mechanism of graphite, carbon components, and the fuel handling systems, we have developed a preliminary technical framework for China's ATGR aging management system. For future directions, we need to establish a more systematic research reactor aging management evaluation system of ATGRs, fully learn from aging management experience of commercial nuclear power plants, strengthen daily aging management implementation, and also deepening research on aging mechanism. Okay, and this is the acknowledgements, and these are the main reference. So thank you for attention.
Thank you very much. Thank you very much. I'll take 2 questions if there's any.
Thank you for your presentation. It seems like quite a challenge that you are facing, and I would like to know, how do you manage this towards the regulator?
You mean for the regulator?
Yes, how do you communicate, how do you convince the regulator that you are doing the right things, knowing that there's a lot of information that you still need to work on?
Maybe for the regulator, I think it's a very good question, because for the aging management system, we have just started to do for the ATGRs. So this is just a preliminary results. So for your question, maybe we should do more research work later. Yeah.
Okay, a round of applause, please. Okay, we are behind schedule, but it will be the last quick presentation. The next presentation is by Abdul Karim. Okay. There you go. Julia Karim, right? She's speaking on implementing the IAEA milestone approach to the Malaysia's multi-purpose research reactor planning.
Yes, thank you very much. So good morning, everyone. So today I'll be presenting on the implementation of the IAEA milestone approach to Malaysia's multipurpose research reactor planning. I'm Julia Abdul Karim from the Malaysian Nuclear Agency. So our agency is a full-fledged government agency under the Ministry of Science, Technology and Innovation. So basically what we are going to do here is we are not a totally newcomer country, because we do have a research reactor, but it was like 40 years ago was planned and was established at that time, and we losing all the documents because of the time evaluation. And for this purpose of presentation, we are trying to adopt on this IEA milestone approach for our new research reactor planning in the future. So here are the agenda. I'm not going through this. You can see that I have 8 agenda here. I hope that I can finish it within the time. Right. For the introduction, Malaysian Nuclear Agency was established on 19 September 1972. So we are now more than 50 years in operation. So Malaysian Nuclear Agency, or MNA, carries 4 main functions. Was stipulated under the cabinet ministerial function. The first one, to conduct research, development, commercialization and innovation in the field of nuclear technology. The second one, to conduct technical support services and training for nuclear and related technology. The third one, coordinates and manage nuclear affairs at national and international level as liaison agency for the IAEA, as well as the National Authority for the Implementation of the CTBT. And lastly, acts as the National Center for Radiation Metrology and Management of Radioactive Waste and Spent Fuel Management. So we have 2 complexes. The main complex land at 60 acres, and the second complex was in 200 acres in the footprint. So we have several irradiation facilities, laboratories, services, and including the research reactor. So here I present you on the National Nuclear Technology Policy 2030. So this document is very important because without this document, we couldn't get funding from the government. So this document was launched on 20 September 2023, it's 2 years ago, and it outlines 6 main focus sectors in medicine and healthcare, food and agriculture, manufacture of devices and equipment, environmental and natural resource management, industrial application, and nuclear safety and security. So the framework of this policy, we have, it's a typical framework. We have vision, mission. I'm sorry, this is in Malay, but some of it in English. And the circle is important, the blue. Sorry. So the blue circle is important because under the strategic thrust 4, it mentioned under advancing research and innovation through value creation. We've outlined 5 strategies. So the strategy number 3 is on the accelerating the acquisition of new research reactor to support a wider range of application with target to formulate and develop a new research reactor program by 2026. So I think I'm in line with this, we are in line with this policy, and with this document, we managed to secure some funding. Right, this is the governance structure of the policy. We have the strategic direction, which led by the cabinet members, with then the blue, I don't know if it's work or not working, it's okay. So we have the National Science Council, which are chaired by the Prime Minister, and you have the High Tech Nation Council, chaired by the Minister of MOSTI. Then you have the coordination. We have 2 committees there. The first one on the National Nuclear Technology Steering Committee and the Technical Committee. So the Technical Committee report to the Steering Committee for any progress or any specific action plan that we have to report to the committee. And then you have the National Collaborating Platform, where you have the interministry that benefit the resources with efficiently. We have the ministry, a lot of ministry, industry, private sectors, and others. Okay, this is what we have currently. We have 1 megawatt trigger reactor, was supplied in by US in 1982. Current status is in operation. The operation schedule from Monday to Thursday and standby on Friday. So this is daily operation with 6 hours a day and 4 days a week. And this reactor reached first criticality on 28 June 1982. By now we have operating this reactor for more than 40 years, and it was licensed under this LPTA/A/1026 by the regulator. In total, we have 31 personnel with 13 certified reactor operators and 5 senior reactor operators. So mainly this reactor was utilized for small production of radioisotopes, short-lived radioisotopes, neutron activation, neutron beam application, and education and training. So you can see that this is a typical setup for TRIGA reactor with 1 megawatt in power. And we receive many samples from the clients, from the users, to irradiate with the neutron for the purpose of neutron activation analysis, and as well as the neutron beam application. So for the neutron beam, although we have 5 beam tube, but more use on the neutron radiography beamline at the radial beam port number 3. And others beam port was used for other research purposes. And we also actively involved in education and training. And this reactor has provided reactor technology education to more than 500 students from various universities, and training around 300 personnel from different agencies. I believe these numbers has been increased by now. And why we are doing this? I mean, why we are doing planning for a new research reactor? So in 2010, we was directed to conduct a techno-economic studies to upgrade the reactor, current reactor, but it turns out it's not economic to upgrade the reactor system from 1 megawatt to 3 megawatt. And spin off from this project, we managed to upgrade several components, structure and components, system and components within this reactor, including to have a new control system from analog to digital, fully digital. And we also managed to build the spent fuel pool for the future preparedness. And of course, this reactor has reached more than 40 years, and it has limited capabilities in producing radioisotope. And the typical lifespan of a research reactor is between 50 and 60 years, and this is a time that we need to have new one. And also we have difficulties in obtaining the TRIGA nuclear fuel. I think this is common issues within the TRIGA users. Right, yeah, so why Malaysia? Again, the question, why is Malaysia planning a new multipurpose research reactor? So it was derived, the decision is not to replace the old reactor, but to make a strategic leap forward. So it was driven by 4 main pillars. The first one, to overcome the limitation of current TRIGA reactor, because it has been 40 years of excellent service, and this reactor has inherent limitation that restrict the potential for growth in nuclear science and technology, because of low power neutron flux limitation, which in turn limits the radioisotope production. So every year we import the radioisotope from foreign country, and this costs us billion ringgit Malaysia, I can say hundreds million of USD. So it's a lot of investment to do. And also with a new multipurpose reactor, this would allow production of wider range of isotopes, including a long-lived radioisotope for medical and industry. And for the research capability, it restricts the complexity and scope of beamline equipments, material, and semiconductor irradiation within 1 megawatt TRIGA capacity. And also, While it was safe and for the trigger reactor, it was safe and well maintained, the system and component are based on older technology. A new reactor would incorporate modern safety features such as digital control system and more efficient operation. So secondly, to meet growing national and economic demands, so this new MPR is envisioned as a national infrastructure to propel various sectors of the economy, especially in the healthcare, industry and food, agriculture, research and innovation. And third one, to build a human capital pipeline for nuclear energy. And of course, I did not mention this earlier. In Malaysia, we have a nuclear power program currently conducting in Malaysia. It was conducted by another agency, but we as the Malaysian Nuclear Agency serve as a we serve for these purposes as well. So the new MPR will serve as living laboratory and training ground, and it will provide hands-on large-scale experience for engineers, scientists, regulators, and operators in managing a complex nuclear facility. And lastly, to fulfill national strategic policy, because the plan is direct and concrete implementation of national nuclear technology policy that I've presented previously. And with this MPR, it's a new flagship project that demonstrates the government commitment to this policy, moving from a small-scale research facility to a major strategic infrastructure that will drive the national nuclear ecosystem for the next 50 to 60 years. And in a nutshell, we are not just building a new reactor, but we are building national capability. So for the project aims, it has four main aims. The first one, to develop an evidence-based roadmap. The second one, to conduct a full-scope nuclear infrastructure assessment to execute the 19 IEA infrastructure issues. The third one, strengthen national capability and sustainability. And the fourth one, enhance global partnership and cooperation. So with this aim, that we conducted a holistic study to obtain new and enhanced advanced information to the government. Right. Okay. And yeah, I forgot to mention here, because this project was funded under the 12th Malaysian Plan, and we secured some budget. So the implementation from 2022 to 2025. Here is the implementation process that currently we are doing the feasibility study for new MPR in Malaysia, and it has been completed and currently in the development of strategic planning for new RR, self-assessment for new nuclear infrastructure and functional specification and site selection. And within this implementation, we coordinate or organize stakeholder engagement with the IEA, feasibility studies and milestone for research reactor project in Malaysia, as Andre was mentioned in his presentation. Right. So we are in this area in the circle, in the square with the circle, in the pre-project project phase 1, to make a justification for the establishment of a new research reactor and consideration before to launch a research reactor project is taken. And for the 19 issues that have been tackled, Malaysian Nuclear Agency was instructed to identify the possible stakeholders and invite them to the workshop. So you can see we have made several stakeholders with, I think, about 63 of them was invited to the workshop. And for the stakeholder engagement workshop that we had with the IEA in June 2023, so the objective of the workshop to obtain information and practical knowledge related to new research reactor using the IEA safety standard and other relevant IEA publication from IEA's own expert. And you can see all the objectives here. And what I would like to highlight on the stakeholder feedback. So you can see that we have about 63 stakeholders coming to this workshop, and engaged very lively in the discussion. So there are several points to be considered in the plan for a new research reactor. The first one, expanding the scope of research reactor to for the energy generation. This comes from the industry stakeholders, from the technology partners. So they propose that Nuclear Malaysia collaborate with technology partners for the construction and operation for new reactor. And from the regulatory perspective, they was mentioned that they can assist in facilitating the licensing process for new research reactor. And there are also a proposal for the government incentive to the private sectors in terms of tax relief, subsidies, or other benefit if there is funding or sponsorship from private sector, and giving emphasis to the public industry, academics, and others agencies. And after that, we organized series of national workshops, such like you can see that strategic planning was held in September 2024, and review of this feasibility study report in 2024. And I would like to bring you for the Malaysian feasibility study in brief. So it was conducted under the contract between the government of Malaysia, represented by MNA, and the company. And this report highlights the background analysis of key factors and a sustainable business model for the MPR technological solution as well as implementation plan. So the objective to evaluate the justification for establishing a new high-performance research reactor in Malaysia, and with the rationale, recognize the importance of developing the MPR as a critical step to meet Malaysia's growing needs. And it also aims to provide the solid foundation for informed decision-making regarding the new project. And for the 19 issues assessment, this is to ensure Malaysia is ready to launch a new project. We've adopted 19 IAA issues, here divided by 3 main categories on the policy and legal, technical, and operational. And for those, it was focused on the IAA project phases, and we are here in a phase 1 pre-project phase for the feasibility study and justification. So from the report, Malaysia's current readiness, it has strength within these 3 items: long-standing experience with Triga Puspati reactor experience, operation and maintenance, and we do have strong legal and regulatory framework, and adequate understanding of nuclear safety and radiation protection. But of course, others aspect we have to improve or increase by now. And the timeline for the project implementation, including decision points and other milestones, we just finished on, I can say that we just finished the pre-project phase, and by this time we are looking into for the INIR-RR request from the IEA. Next project, phase 2 and phase 3 will follow after the phase 1 has successfully completed. And for the way forward, there are several planning in a pipeline. The first one, to conduct the symposium of neutron utilization using research reactor with the participation from stakeholders, mainly presentation on neutron utilization in core beam experiment and future application using the MPR. And we also perhaps have site survey, site selection, and evaluation was planned in next year to have the siting program planning. The next one, to establish a communication plan through the DTNN strategy or platform. And the next one, continuous education and training for HR development in next year. We hope that we could invite IEA for the NPHR planning for the expert mission. And also we have submitted budgetary for a Malaysian plan on the 17th September 2024. So for the conclusion, so you can see that Malaysia is building on a 40-year legacy of safe reactor operation. So new multipurpose reactor is strategic national project aligned with the DTNN 2030. And IEA milestone approach provides an indispensable structured framework for success, because we would like to have this program or this planning smoothly taken. And this methodology ensures robust planning, stakeholder confidence, and long-term sustainability. And we are committed to localizing international best practices for our national context. So thank you very much.
Thank you very much, Julia. I'll take one question, then we close. Okay, we all want a break. One round of applause for the colleagues, please. So it's now 12 minutes after 11. Can we please come back around 11:25 for 11:30, please? Thank you very much. Let's adjourn.
Try two. Okay, let's settle down. Let's settle down to begin the session. Good morning, colleagues. My name is Emmanuel Boafo from the Ghana Atomic Energy Commission, and I'm your chair for this session on research reactor safety. Safety is important and critical for us, and also a key pillar, one of the key pillars of this conference. And so we'll hear from our distinguished colleagues and experts on various aspects of research reactor safety. So the plan is to have all the presenters finish their presentation. We will save some time on all the presentations, and then we will have a short Q&A after all of the presenters are done. So while they are speaking, if you have questions, kindly note your questions, and then when they are all done, you direct the questions to the individuals that you desire. So to start off, we want to take our first presentation from Ms. Farhana Nasser, who is going to give us an overview of IAEA activities in the area of research reactor safety. So let's welcome Ms. Farhana Nasser to begin the session.
Hello. So, good morning. Hello, yeah, this is fine. I'm Farhana Nasir from Research Reactor Safety Section of the IAEA. I will be presenting the activities and some safety issues as well as the challenges for the research reactors. First, the introduction. I will skip the overview of research reactor, but one slide is important. I will go with this because our colleagues Ruben and Andre has also covered the introductory part. Safety issues and challenges that we received from the member states, and then we built our program and activities on the basis of those issues and challenges. I will also cover the IAEA program of activities for research reactor safety, and I will conclude with my remarks and the upcoming activities for the next years. Our research reactor safety section is supporting member states in achieving and maintaining high level of safety for the research reactors. Our section also deals with the safety of the fuel cycle facilities, but with the different staffs. And for the overview of the research reactors, we were discussing also in the previous session about the aging problem of the research reactors. About 2/3 of the research reactors are more than 40 years old, and 40% of the research reactors are 50+ year olds. That was the basis for the IAEA Code of Conduct on safety of the research reactor. That is important document I will cover in my upcoming slides. The Code of Conduct, which was the reason for the development of the code was the aging, and also many facilities were in the extended shutdown conditions. So the extended shutdown condition after the implementation of the code was reduced about 90%, and those research reactors which were neither operating or they were in long extended shutdown conditions, they were either decommissioned or come back into operation. The feedback for the issues and challenges, we received this feedback from our Code of Conduct meetings, as well as from our incident reporting system for research reactor, and also with our review services as well. I will cover all this feedback next. The Code of Conduct meeting, we conduct it internationally every 3 years. And the last meeting was in 2024. For this Code of Conduct meeting, we asked the member states to provide us the self-assessment based on each of the code provisions. And the code provisions are linked to the safety requirements as well. So it is really a good document for doing the self-assessment. I will cover this document because same is also the self-assessment is used for performing the before performing our IAEA peer review services. With the regional meetings we planned on the issues of common concerns within the region, and we also receive feedback from the regional meetings. This is the feedback. I will not spend more time on this because it is from the Code of Conduct meeting. We get the self-assessment, we analyze that self-assessment on the basis of the code provisions. The code has the provisions for the state regulatory body and operating organization, with the part for the IAEA responsibility as well. So with the previous years member states who were participating in the code and submitting the self-assessment reports, this was the data, and it shows that from the previous meetings there was slightly improvement in the implementation of the code provisions. When we made the analysis to identify the areas that needs improvement from the previous years, like 2014, 17, 21, and 24, there were common member states who were attending the meetings, about 23 member states. And for the last meeting, there was 32 member states. So we got the picture after the analysis as the safety areas that needs improvement. And most of the highlighted parts were related to the financial human resources. And then leadership management seems to be the highest priority with the member states. And then information on the improvement of the aging management programs and other like the operation and design and upgradation of the facilities according to the safety standards. We get similar response from the feedback that some of the member states source of information they are facing the issues and challenges for the development or for the decommissioning planning. The feedback from the incident reporting system shows that we analyzed the data from the incident reporting system. This data is related to the incidents happening at the research reactor, and national coordinator reports to our incident reporting system database. We analyze the data sent by the incident reports from the member states, and it shows after the analysis that about human errors is 30%. Most of the incidents happens with the human error. Then the aging of the facility was also issue with the 30%, and remaining were the management of safety and design quality assurance. We published the revision of the tech doc in 2024, and we analyzed the data till May 2022. And this document is really useful because we did not share the facilities information, but the incident reported to the IAEA, IRSRR were shared. So we got this feedback. And then the next feedback is from our INSAR missions. INSAR missions are the peer review services that our research reactor section provides through the operating organization of the member states. We analyzed the INSAR missions recommendations, and the basis of the recommendations, some areas were identified as challenging because several recommendations were made on these areas. These were related to the leadership and management, the safety culture aspects, and there was some improvements in the SAR or OLCs, and the upgrades implemented after the Fukushima accidents, and ultimate decommissioning was also most recommended topic for the INSAR missions. So on the basis of the feedback and the areas of issues and challenges, with our research reactor safety section approaches that we provide peer review services on the request of the member states, the capacity building activities, including self-assessment, information networking, or the regional international networking, and also the complementarily the TC Technical Cooperation Program, extra budget program, and our research reactor safety section also disseminate the information on the experience of the member states. The code of conduct that I was mentioning covers that it is a guidance level document, not the safety standard, but it is very good document for the guidance of the member states, and the member states can use it, the wording they can best accomplish through their national regulations. They can incorporate into their own framework. And IAEA disseminate the code related information. We collect the information in the form of self-assessment and disseminate that information as well. We also provide the services for the application of the code, and with the applications of graded approach depending on the facility as well. The main responsibility or the activities of our research reactor is the safety standards and supporting document publications. The main requirement that is for the research reactors is SSR 3 on the safety of research reactors. Then there are some supporting the safety standards in the form of the specific safety guides that we have published. There were 11 safety guides after the revision of the SSR 3. All of the 11 safety guides are updated on the basis of the new requirements introduced into the SSR 3. And these are the guides that we published, and it covers all the areas of the research reactor safety. Then we also publish the supporting documents in the form of tech docs and safety report series and the training material as well. That is useful. Our research reactor safety section further activities are the conducting the INSAR missions. We have two services guidelines available for this. One for performing the self-assessment before the INSAR mission, and also for the code of conduct. The same document is used, that is services series 35. And for performing the INSAR missions, the guidelines are provided into the services series 25, and it is recently updated. The other peer review services and advisory services related to the continued safe operation of the research reactors. We adopted the SALTO mission. First it was only for the nuclear power plants, but now we are conducting it for the research reactor with the using the guidelines. And we have conducted missions for Belgium, Netherlands and Uzbekistan, and follow-up mission was also conducted for the Netherlands. Then the peer review services we provide for the periodic safety reviews. IAEA supports implementation of PSR. Previously, the guidelines that was used by the member states were SSG 25, but that was mainly related to the nuclear power plants. So this safety report series is issued for the PSR of the research reactor. We also organize the workshops and the meetings for the to cover this topic of periodic safety reviews, because this is also the topic where member states are are having challenges. The other activities of our sections are related to the project and supply agreements for the research reactors. And we monitor these research reactors for collecting, analyzing, and disseminating the results of the safety performance indicators. These research reactors are under project and supply agreements, and we conduct regular meetings to get the feedback for the SPI safety performance indicators from research reactors. Then for the capacity building activities for education and trainings, we conduct group fellowships, training courses, online training material is available, the coordinated research projects and support to the TC programs and information networks. These are the two CRPs currently. That is our section along with the Annie, Ruben Mazi, our colleagues from other IAEA section. So these are the two CRPs ongoing. And then for the dissemination of operating experience, I covered this tech doc. We maintain the database. About 64 member states have joined this database. More than 95 of the facilities are covered by these countries. And we published this in 2024 in the form of the tech doc. For the new research reactor, or the countries who are establishing the new research reactor in coordination with our other research reactor section from nuclear energy, we conduct some activities, and the advisory services we provide in the form of the project management, regulatory infrastructure, licensing process, and other such as commissioning program, preparation of the routine documentations related to the safety. Then the research reactor activities under TC, who support the implementation of several tens of national and regional technical projects. And we support the functioning of the regional advisory safety committees. For example, for Europe, Africa, and Asia Pacific region, these committees are called RASCA, RASCAP, and EURESC. And we support the functioning of these regional advisory safety committees. We also support the functioning of the information network, such as for the Africa, it is FNRBA for the regulators, and also ANUR for the Arab countries. For research reactor activities related to the support to member states for improving their regulatory supervision, we have the developed training material that member states can use for the training of inspectors, inspectors of the regulatory body. The practical training on the regulatory inspections, we provided workshop almost in all the regions. And for inspection program development based on the IEA safety standards, we have provided guidance to the member states for the establishment of the inspection programs, such as Morocco and Jordan. And then we also provide training and assessment for the regulatory bodies performing oversight of the research reactor. The major meetings and workshops for the future. For the next year plan, there is a regional training activity for the Asia region from 9 to 13 February on safety analysis of research reactors. Technical meeting every 2 years we do that. It was this year, last year conducted, next will be in 2026. All other activities such as the workshop important for the self-assessment is also planned in the next year, and safety of experiment is also planned. For 2027, some of the activities are planned in which under project and supply agreements. This year we conducted this meeting, next will be 2027. The code of conduct meeting also, and in the technical meeting of national coordinators of incident reporting system every 2 years. Next is planned in 2027. And then the international workshop that was last year, it is planned in 2028. So I will conclude my presentation here, that we continue supporting member states with through the development of the safety standards, as well as by the peer review services and capacity building activities. And then regulatory effectiveness, we provide supports to the regulators for embarking countries as well as the expanding countries as well. Then also we provide supports for sustaining and improving the international networks, for sharing of knowledge and experience, operating experience as well, with the good practices among the member states. So these were the activities that our research reactor safety section performed on the basis of the safety standards, as well as the issues and challenges being faced by the member states. So thank you.
Thank you, Ms. Farhana. So as I said at the beginning, kindly note your questions, and at the end of the session, we have a Q&A, time for Q&A, so that you can ask your question. We move to our next presentation, and it is on operation and relicensing process of the Maria Research Reactor by Witkowski Piotr. Please, Mr. Piotr, you have 15 minutes to present.
Good morning, everyone. My name is Piotr Witkowski. I am I am a reactor Maria manager from 5 years. And I would like to, after the presentation from tomorrow morning, I would like to present our approach to extending the time of operation of our research reactor, because actually we don't have plans to build the new research reactor in Poland, but we would like to provide a safe operation. Reactor Maria is operated by National Center for Nuclear Research. It's one of the biggest scientist center in Poland. We have a nuclear physics science, also radiopharmaceutics, also facility to produce radiopharmaceutic, and we produce accelerators. Reactor Maria has a quite unique construction because we have two separated cooling systems. One is dedicated only for fuel channel, and second one is dedicated for reactor pool. Moderator in our reactor is water, of course, is water and beryllium blocks put between the fuel, and core is surrounded by graphite reflector. Actually, we have a license, and we are using two types of fuel, MC5 and MR6. This is uranium silicide and uranium oxide, low enrichment, both is low enrichment fuel. Maximal thermal power is up to 30 megawatts, but we have a limit to maximal power per the fuel elements. It's 1.9 megawatts from one fuel, and the thermal neutron flux in the channel of irradiation is 2 and 10 to 13, and usually we operate a reactor over the between 4,000 and 4,500 hours per year with nominal power. This is a scope of history. The start operation of our reactor was in 74. So it means that in the previous year we have a 50 anniversary of 50 years of operation, but between 85 and 93 we have a quite long first maintenance break. During this break we upgrade cooling systems, add the safety valves, prepare a modernization of ventilation system. The next in 2000 we have a modernization, the first modernization of INC systems. In 2004 also we had a 1 year break in operational. It goes lack of fuel, the new fuel for our elements. Between 2009 and 2015 we have a process of fuel conversion from the HEU to LEU, and in 2013 we had a modernization of the fuel channel cooling circuit. It caused the conversion of fuel because we use the new type of fuel with different construction, so it was needing. And in 2022 between and 2023 we have a 1 year break of operational. In operation it caused the modernization, and in this year we get the new license. I add later about it, and we would like to operational up to 2015. This is a cross section of our reactor and spent fuel. The reactor is under 7 meters of water. We have 7 horizontal channels, and next to reactor is a technology pool with spent fuel and access to the hot cell, underwater access to our hot cell. This is also the figure of our reactor. Okay, oh, this is the different version. Okay, this is the scope of operation of our reactor. The average working hours is about from 4,000 to 4,500 per year. As I said, in 2022, between 2023, we had a break in operational. It goes the modernization. The length of cycles is between 100 and 215 hours. And usually we use about 15 fuel elements per year. This is a schedule of our operation. As I say, usually reactor is operated in short cycles in the comparably with different reactor, but we have access for the irradiation the most of irradiation samples only when the reactor is shut down. During the operation with nominal power, we have only hydraulic rubbish system, not allow to access to the all channel. These are some safety performance indicators from the last years. The dose and radiological protection is quite good. In the past, we had some problems with plant shutdowns, but we resolved the most of this problem, and actually the situation is good. And here is the main scope of our utilization. This is a production of radioisotopes. This is a main goal of our operation. We irradiated tellurium, samarium, lutetium, ytterbium, cobalt, minerals, holmium, and many different isotopes. Also, we irradiated uranium plates for the production of molybdenum, but we don't have a own facility. We sent targets to Netherlands, to Curium. So also we have equipment to irradiation in the fast flux neutron system, fast flux equipment. We have a quite big. We can put quite big samples for put in the next to core, and we have a special blocks to create to cut the thermal neutrons and to create only high energy radiation with high energy neutrons. What we done in the previous years, it was related scintillators, electronic components, dielectrics, and ITER windows. And after the irradiation, we had some examination in our hot cells. Also, during the last years, we improved our experience in high temperature irradiation facilities. The first one rig was equipment to irradiation with graphite samples in 1000 degree. It was the electric heating and nuclear heating. The temperature was provided by the isolation between our pool and internal tube, and was irradiated for 35 days. Also, we have some experience with electric components examination in a different temperature. We checked the radiation for the degradation caused the radiation of this equipment. And actually, during the last year, we have a testing pressure sensor and temperature in 200 degrees. Also, the other utilization. We have a neutron beam ports, but during the last, we have our experimental hall is during the modernization, so we don't have any testing. the training also as we are only one research reactor in Poland, so we have some training for the reactor physics and technology employers, but this activity also is reduced for the situation in Poland. And during the last year, we was covered a quite big modernization to exceed the time of operation of our reactor. We had a program dedicated to modernization of our reactor. The main factors taken into account to developing this program was aging, lack of spare parts, improvement of nuclear and fire safety, because in the previous year we had some review in Europe, and we want to improve our safety, fire safety. The second, also the cause was redundancy of measurements, compliance with safety standards, and affect actual atomic law in our equipment. And also the last one was recommendation from the OMAR missions, because 3 years ago we had in our reactor OMAR missions, and we had a few recommendations, and we would like to improve that. The modernization took a lot of systems, the most of system of our reactor, from INC system, neutral measurement system, reactor protection system, rod drive mechanism. It was do in one part because it's straight connected connection between these systems. So it's the biggest, I think, the work during this modernization. Also dosimetric system, fuel leakage detection system, because in this case we are using the old controllers, and we should replace for new version. Also, we should improve the chimney relays measurement system because it's quite old, and to fulfill actual standards, it was needing. And what we did, we replaced as we see on the picture, we replaced cables and electrical supply equipment to improve the fire safety of our reactor. It was done, so we replaced about 70 kilometers of cables, so it was also quite a big job. What we done also, we replaced and modernize our radioactive liquid tanks, as we see on these pictures. It was also a quite big construction work, because according to the atomic law, we should have a double sealing the tanks, and it's needing to replace and smaller modernization, like reactor pool cooling system, the pump, water recirculation system, secondary cooling system, and ventilation system with fans and carbon fibers. And the last of our activities from this year, it was the most important, was the license, to get new license for operation, because the reactor was licensed up to now every 10 years, and actual the previous license was up to end of March 2025. So during this period, we made 2 periodic safety assessment. It was a very short time to do it, and it was very difficult to do it, but we finished and start agreements with our nuclear regulator in the beginning of 2024. But the whole documentation we sent in August previous year. According Polish atomic law, regulator has a half year to check these documents and to get. But yes, in the case of complicated of case, it could take longer. But finally, we get a license in end of July this year. But but we have the 4-month break without a license. It was very difficult time for us, because this time it isn't allowed by law, because we don't have reactor could be during the building, in operation, or the commissioning, and this status was quite different for us. And according to our regulator, we can do we could do only necessary work, what is necessary for the safety view, not any different things during this time. The most important documents what we should send to our regulator was, of course, safety analysis report, emergency plan. This is the most difficult documents, because we should create the external emergency zones for the worst case scenario. And this emergency plan should be agreement and consult with firefighting, police, and local administration. So every changes in this document impact for the next consultation. And of course, also we had a safety classification of structural system components. This takes it takes a lot of time this document we did for close 5 years. So because we should do according law for nuclear power plants. So it was a very challenging for us. We had a more than 1,000 different groups of components. And for this classification, also we had prepare the maintenance and testing and supervising program, aging management program. Also, this tool was connected with a safety classification. So significant changes in our classification impact to the next document. So also it was quite difficult. This free document and different, so much easier to fulfill requirements. It was integrated management system, quality assurance program, training plans for reactor operators and employers, and decommissioning program. Oh, this is about our emergency plan. We should create the external emergency zones for for the worst case scenario, and this takes a lot of time to argue. And thank you for your review.
Thank you. So again, we want to keep our questions, note our questions, and at the end of the session, we will have time for question and answers. We want to take our next presentation. We have 2 more presentations from yesterday in this session, so please let's try to keep to the time so that we have some time for the Q&A session. So our next presenter is our host, our able host, who is going to talk about Safari 1, SALTO, and PSR approach to justify long-term operation beyond 60 years. So let's welcome Mr. Samson Malaka to give us a presentation.
Thank you, Chairperson. They wrote my name, the one that I don't like. It's on my ID. My name is Semi Malaka. I prefer Semi Malaka. It's fine. Thank you, no problem. It's just a light moment. All right, colleagues. Good afternoon. I think it's 12:10. I would like to share our second last talk from Safari. This one will be about the Safari 1 SALTO, which is safety aspect of long-term operation, and a combination of a periodic safety review to justify operation beyond 2030. The outline, I think the brief overview, I'll just run on it. Yesterday I did present the brief overview of Safari. Then I'll outline the problem statement and then the main aspect of the LTO program for Safari, our PSR and LTO strategy, and then I think I've also presented the timelines or the milestone, and then I'll conclude. So I think in this slide, the most important aspect is that, ladies and gentlemen, Safari for the past 60 years have never conducted a formal PSR. So this is our first take to the PSR. So, but however, indeed, what we did in terms of the safety assessment, we did conduct the plant SSC health status assessment and also the reactor vessel assessment, as well as the biological shield. And then we have been presenting that to our regulator on a periodic basis as a safety justification for continuous operation. But then I think the problem statement on the 26th, I think, of March 2024, we have our license revised. And then when the revision of our license is called the NIL 02 Nuclear Installation License number 2 for NECSA. When it was revised on the 26th of March 2024, it has an authorization limit. That authorization limit, it was set at 31 December 2030. So we aspire to follow the LTO regulation as espoused by our national nuclear regulator for us to extend the license beyond 2030. So what we will do an application in terms of the National Nuclear Regulator Act, and then we will conduct what we call an LTO. Yesterday I indicated LTO, normally I think it's associated with the nuclear power plant. For us, it's a CSO, it's continuous safe operation. So in that, the requirement is for us to present a safety case to the regulator in support of our license extension. So I think we have completed, ladies and gentlemen, what we call a PSR basis document. Our basis is that for the 60 years of operation, Safari had an impeccable safety record. There has never been a fatality in terms of our operation. We have a comprehensive aging management program. I think Ms. Dolo said we have implemented it. It follows the Atomic Energy Agency guideline in ensuring operational availability and nuclear safety. And we have upheld that for the past 60 years. And then we have performed, as I've indicated, the ongoing reviews to ensure continuous safety in terms of the improvements. Also, as is typical with most research reactors, Safari does not have a design life or a service life. And then I think we have commented in terms of the design life. Safari does not have a design life only if we can substantiate continuous safe operation. So, okay, I've alluded to the license condition, the expiry. Therefore, a license application is required in terms of the NNR Act for us to motivate continuous operation beyond 2030. So for this license application, what we are going to do, we are going to provide the regulator with what we call a periodic safety review to justify our long-term operation. And I think this is enshrined in the NNR Act, as I've indicated, is part of the long-term operation regulations. Then I think the PSR will be conducted as per the EIA guideline. We will use the known EIA guideline, which is the periodic safety review for research reactors. I think it's series number 99. So in terms of the formulation of our PSR basis document, we have followed the SR 99 to the latter. So the objective for our PSR first is to demonstrate the adequacy and effectiveness of both our processes and procedures, as well as our structure, system, and components to ensure that they can carry us in the period of the LTO, which we envisage to be 10 years post-2030, which it will be up to the 31st December 2040. So our strategy is four-pronged. We have completed the feasibility study where we looked at the techno and economic assessment, ensure that there is adequate project funding as well resourcing. And then we've completed the feasibility study. So the second phase is the periodic safety assessment. So what we did here, we have combined what we call a PSR basis document. We have completed it. We are planning to submit to the regulator at the end of November 2025. Then I think the third aspect, we have already engaged and secured the expertise from the International Atomic Energy Agency in terms of the SALTO mission that Fahana has presented. So we will have this SALTO mission at Safari in February 2026. We have done a lot of work in terms of the self-assessment and the preparation for that mission in terms of the whole review. Then the last aspect is for us to compile. After we have done the periodic safety review work as well as the SALTO work, we will compile those gaps in terms of the safety case, and then provide the recommendation from both the expert and then subject our safety case for an independent review before we submit to the regulator. So in terms of the SALTO, I think I would skip this slide. I think Fahana just indicated this is a peer review mission, which is actually provided by the EIA. So if you look the main contribution of the SALTO mission, I think they are listed there. So we will look into compliance on the existing regulation as well as the aging management aspect. I think most of the items on there I've alluded to. We have done comprehensive work as far as the aging management review is concerned. So the other work that we are really embarking on very tirelessly is the TLA. I think Sejako Tolo yesterday indicated how far are we in terms of that process. It's part of the aging management review as part of the safety justification for our long-term operation. Okay, then I'll skip this. It's a repetition. And then I think this is basically for those who are not familiar in terms of the PSR for research reactors. So we've got about 14 safety factors. So we have assembled team to look at all individual safety factors and provide the safety factor reports. So as part of the regulation, I think if you look on my right, so this is the expectation from the regulator. We will start with the LTO application, then it will be followed by the safety case, and then it will follow all the steps until there is a NNR safety evaluation of our safety case. And then on the other side, there will be what we call a public participation process, which will subject our aspiration for long-term operation. So we have established the safety case framework. We have established the development part as far as the safety case. So after we've compiled it, we will subject it, as I've indicated, to the independent review before submission to the regulator. So I think the main elements of our LTOs, ladies and gentlemen, I think one, we have finished it. We've got a proper licensing strategy, which will be accompanied by what we call a project management plan, and then a application itself, and then the PSR basis document. What I need to highlight, I think, in this slide is to indicate to you that our regulations, because we've got an existing nuclear power plant, so our regulations are so heavy because they are inclined for the 2 reactors that we are having for nuclear power plant. However, we have applied what we call a graded approach so that the hazard and the concerns are suitable to a research reactor facility. All right, I think this is a typical structure that we have used in order to populate the work for the LTO. I think at the back we've got Ms. Mulalo, who's actually our program manager for this work. So what we did, we've got a feasibility leg, we've got the PSR leg, we've got the SALTO leg that is being, and then there are licensing engineers, and then from the facility, the operation and maintenance in terms of the aspects to support the safety case. And then we've got some on site, we call them the safety case engineers, as I think one of the speaker alluded is very important. That's a difference between licensing and safety analysis. All right, I think I've shared the milestone. We are hard at work to ensure that we don't slip up. So we are envisaging that by the first quarter of 2028, we will have actually completed all the work that is required for submission to the regulator to allow. If you look at the last slide, the regulator need amount of 42 months for them to properly review the safety case before they can actually pronounce on a decision of our license extension. I saw on my colleague here next door, he indicated that they stayed 4 months waiting for regulatory approval. So we don't want to find ourselves in that. So we have allowed for 42 months to submit to the regulator in terms of ensuring that they've got the adequate time to review our submission and then provide a determination. So I think in conclusion, I've talked about the feasibility study where we have done the techno-economic assessment, and then we had that initial engagement with the regulator, which I think went well. So we understand what needs to follow in terms of the process. It will be a license application, which we have now compiled. It's a PSR basis document, which we have now finished. So it will be submitted to the regulator at the end of this month. Then we will undertake a SALTO mission, which is a peer review mission, as I've indicated. And then from there, we will compile our safety case document. And then we will importantly subject it to the independent review. Even our PSR basis document, we have subjected it to the international peer review. So it's a peer-reviewed basis document. Then I think as the last step, then we will ensure that we complete all the prerequisites of the LTO, depending on the comments that we receive from the regulator, so that we allow that review process for an LTO decision or the license extension. Then I think, finally, I think what is important, colleagues, is to say the successful execution of the PSR is very extremely important for the Nexa operation. So we will ensure that we meet all the regulatory requirements to ensure that come 2030, the license is actually extended for another 10 years to 2040. So as Safari, we believe that by combining the PSR approach and the independent SALTO review process, the facility will present a robust, transparent, and then an internationally recognized demonstration of safety and a firm commitment to safe, continued operation of the Safari Research Reactor beyond 60 years. Thank you very much, Chairperson.
Thank you very much, Sami, for that insightful presentation. Please note your questions, and at the end of the session, your questions will be addressed. So we've heard from the operator. We now want to hear from the regulator. And so I have the pleasure to welcome Ms. Palesa Ramego as she presents on Safari 1 Research Reactor Regulatory Oversight by the National Nuclear Regulator, NNR. Please welcome her.
Okay, thank you. Sorry. So I have my colleague here who is going to present the licensing process. So makes sense if he goes first. Yeah, for him to go first. And then I'll go after.
Okay. So let me. So we want to hear from Lindile. Okay. So Lindile will present on the NNR authorization process, ensuring nuclear safety and regulatory compliance in South Africa. So let's welcome Lindile.
Thank you. Good afternoon, everybody. My name is Lindile. I'm an analyst with NTWP Assessments. I'll be presenting on the NNR authorization process. So I'll first give a brief introduction, give you the regulatory approach to licensing, and then get into the meat, which is the authorization process, how we go about doing that, and then conclude. The NNR was established under the NNR Act in 1999 with a mandate to provide for the protection of persons, property, and environment from nuclear damage. And it achieves this mandate through the authorization process that I'm presenting on today. So these four are the main functions of the regulator. We develop regulatory documents, and then we issue authorizations based on an applicant showing compliance to those developed documents. And then the way we actually issue these authorizations is through reviews and assessments and compliance inspections and enforcement. So yeah, in the next section, I'll go through the regulatory approach. These are the topics. So first, it's the philosophy. Our approach to licensing, it's a combination of risk and performance-based factors. So we set overall safety goals, and then the applicant then demonstrates to us how they're gonna meet those goals, and then we hold them to their justification. Our process is technologically neutral. You decide what technology you want to use, and then you show that it complies with our requirements. And then a dualistic approach requiring both design basis and risk analysis. So this is the legal framework within which we operate. There's the NNR Act, Energy Act that established NEXA. We've got regulations that we've drafted. I think currently the ones that are active is the SSRP, and then we're in the process of finalizing the general nuclear safety regulations. There's also environmental regulations from Department of Forestry, Fishery and Environment, and then also our international safety standards by the IAA. So yeah, the objectives of the process is to ensure safety, first and foremost, is to foster regulatory compliance, environmental protection. Also now, it's to foster transparency and accountability for the public, because at the end of the day, that's who we serve. We also promote safety culture to ensure that the operating organization prioritizes safety above all. These are the types of licenses that we issue. Nuclear license. Okay, these are as per the new act that was revised. A nuclear license, I think Safari, that's what they have. A nuclear vessel license for vessels that are prepared or propelled or contain nuclear material. Certificate of registration, these are applicable to mines, scrapyards, and so on. Certificate of exemption, also applicable to mines, those who are where the material is below exemption levels. A certificate of design package. Currently, these are issued to, I think, Kuberg, NTP, and Safari through one of their licenses. And then also authorization to manufacture, that one is new according to the new act. We have yet to issue one of these. So when an applicant applies for an authorization, they can choose to either apply for one license covering all stages up to operation, or they can decide to apply for different stages. You can apply for a site license, for instance, get approved for that, move on to design, move on to manufacturing and construction and so on, or you can apply for a combination. You can apply maybe for licensing site at first, then apply for design and manufacturing as one combined license. And in each stage, you must have an accompanying safety case. And then, yeah, we'll review that, and then conditions are issued. So in the case of one license, we will have hold points where we'll have to check compliance to certain requirements before you can move on to the next stage. I think one that we can talk about is when you are moving from construction to commissioning, we need to have certain hold points there to check, have you, like your supplier qualification, was that done accordingly, and so on. Yeah, in those stages. Then now I'll get to the main part, which is the authorization process. I think in the interest of time, I might skip some of these slides because I'm going to cover them at the end in a process diagram. So first, if an applicant is not familiar with our requirements, they can call for a pre-engagement, a pre-application engagement, where we can clarify our requirements. Then, yeah, they can identify potential technical issues or safety issues, and then they can do this through letters or through organizing meetings in person or via Teams. So an application must be submitted. I think there's a format in Government Notice 1219. So when you do submit, you must actually, provide usually the name of the applicant, address, physical, postal. If it's a company, you need to know the company registration, who is the point person. So the board must issue a certificate of delegation to say this is the person who can make an application on behalf of the company. And then, yeah, it should be accompanied by a safety case covering the topics indicated in the slide, amongst others. I think Mr. Witkowski actually covered some of the safety case documents required in an application. So yeah, during our technical evaluation, we look at some of these topics: design, operational safety, radiation protection, environmental protection measures, your security and emergency preparedness. And also some of the things not indicated here that we look at, it's the competency of your staff. We look at your IMS, QMS. We also look at your waste management considerations. Are you going to be producing waste that you can't dispose of? You know, those kind of things. And then, yeah, during the process, I think as per Section 21 of the Act, depending on the license you're applying for, there needs to be a public engagement process. So you are directed to serve a notice to the public, publish your application, and then, yeah, it initiates that process. There's one of our RDs that covers that. I think I'll speak more of this when I'm going through the process flow diagram. And then an application can be granted, deferred, or denied for various reasons. These are communicated to you by the CEO. And if you are unhappy with the decision, or if the applicant is unhappy with the decision, they can, I think there's a section that covers appeals to the minister, to the courts. Then, so once the license is granted, there will be conditions that are imposed on the applicant. And then we'll also be conducting regular compliance assurance inspections. We'll also be monitoring radiation doses, environmental discharges. My colleague Palesa will actually talk to that. And then this is the process diagram that I wanted to tell you about. So let me see. I'm not sure if you can see this. So we received the application. It is registered at the CEO's office. It is then communicated to the relevant program manager. It is then reviewed for completeness in terms of that government notice 1219 I indicated. If there are any deficiencies or maybe there's missing information, it is sent back to the applicant to actually request that. If everything is fine, we then acknowledge the receipt. We then evaluate it and communicate with the board that we've received such and such an application. On their side, they then decide whether is it supposed to go for the public participation process. And then this process actually happens in parallel with this one, the reviews and assessments that I'll talk about just now, because we need to actually review your safety assessment before you publish. And then so it is then sent to the reviews and assessments department. I think I'm working under one of those NTWP assessments where we review your document based on those factors I indicated earlier. And then if there are any deficiencies there, it is communicated to the applicant to say, yeah, either you're not complying with this and this requirement, or we need this supporting documentation. Then it is sent back to us, we review it. And then if your safety assessment is adequate, you are then directed to prepare a PID. Mr. Malaka actually talked to that at some point. That PID is published along with your safety assessment. It is then reviewed by the public. We receive comments. Based on the comments, we then decide, the board actually decides whether public hearing in such a platform are required. If not, then we prepare a safety evaluation report. If they are required, we conduct those. Based on the applicant's responses, we then conclude our review. We compile a safety evaluation report with either outcome, be it negative, positive. The board then decides whether to issue the authorization or not. Depending on the outcome, the CEO then indicates whether is it positive outcome, negative outcome, and then the applicant is then free to appeal if it's not positive. So in conclusion, our authorization process it's our cornerstone for nuclear governance. By integrating technical evaluation, regulatory compliance, environmental protection, stakeholder engagement, we are able to ensure safety of nuclear operations. And then also through ongoing oversight, promotion of safety culture, and adherence to national standards, the NNR can actually strengthen public confidence. Yeah. Thank you very much.
Hello again. Okay, I'm just waiting for the presentation. Okay. Good afternoon. My name is Palisa, and I'm going to be presenting on the regulatory oversight of Safari Reactor by the National Nuclear Regulator, that is the NNR. So my presentation is going to begin with an introduction where, some of the things will have an overlap with the presentation you just saw, but basically introducing the NNR and who Safari is, and then I'm going to go through the regulatory framework and philosophy, which underpins all of the NNR's activities. Then I will look at the NNR regulatory oversight of Safari, looking in particular at the waste generation and discharges to the environment, and the site-wide doses to workers and the public, and then I will discuss some trends and key takeaways. So to begin with, the NNR is a public entity which was established by the NNR Act in 1999. It has since been amended. The NNR is responsible for the protection of people, property, and the environment against nuclear damage. And as such, it regulates a diverse range of nuclear installations, all of which are capable of causing nuclear damage. So these include nuclear power plants, research reactors, and radioactive waste management. And the NNR fulfills this mandate through a regulatory framework that's based on national laws and international standards. And as you guys know by now, Safari is a 20 megawatt research reactor that has been operational since 1965. And given its nuclear nature, it is regulated by the NNR, and its license is NIL 2. So to get to the regulatory framework and philosophy, the NNR's regulatory framework is based on the NNR Act, as I mentioned before, and also the regulatory standards, in particular the Regulation 388, which is the SSRP, and it's based on licensing conditions, which are basically defines the obligations of a licensee. And we also have international standards, so we align with the IAEA's safety framework, and we ensure compliance with which ensures compliance with global best practices. So to go to the NNR's regulatory philosophy. So the NNR applies a risk-based or risk-informed and defense-in-depth regulatory philosophy, which essentially means that we apply our standards on a case-by-case basis, depending on the nuclear installation or activity's risk, the risk that is associated with the installation or activity. This emphasizes preventing accidents through robust design and operation. We seek to ensure multiple layers of safety, which includes technical, procedural, and human safety measures. And then we also look for the licensee to apply the ALARA principle, which essentially means keeping the radiation doses as low as reasonably achievable. And the NNR also seeks to promote a strong safety culture among the operating staff of the licensee, which essentially means that the staff members live out safety themselves, and the NNR also uses data-driven oversight to focus on safety significant areas. As Lindile mentioned, the NNR gives out licenses to the licensee, and for this license to be given, the licensee or applicant must have a safety case, which addresses design-based accidents, operational limits, and emergency preparedness to demonstrate to the NNR nuclear safety. Additionally, there are periodic safety reviews to confirm ongoing compliance with evolving standards. And then the licensee has to ensure compliance to its licensing conditions, which cover staffing, training, safety analysis, and waste management. And then when a licensee seeks to modify or upgrade they have to submit these modifications and upgrade to the NNR before implementation to again ensure that there's going to be nuclear safety. The NNR's compliance and assurance activities they ensure this through planned, unplanned, unannounced inspections, and also, as Lindile mentioned, document reviews. And to ensure compliance, when non-compliance is identified, the NNR applies enforcement measures through imposing licensing conditions restrictions until safety requirements are restored. So this can include limiting the operations. Also they require formal root cause analysis for safety-related events, and in extreme cases, suspension of operations. Next, I'm going to go through the oversight of SAFARI by the NNR, looking in particular at the waste generation and discharges to the environment, and the doses to workers and the public. So, as part of the licensing requirements, SAFARI 1 must monitor and report on the radioactive waste generated, which includes the accumulated fuel. So the graphs on the left-hand side are firstly the radioactive waste generated, and the one at the bottom is the accumulation of used fuel, and this is for the years 2021 to 2024, and the blue at the top is the low-level waste, and the orange is the intermediate level waste. Next, this is the discharge to the environment. So the first graph 5, shows the liquid discharge versus the limit in terabecquerels per annum. And the one at the bottom shows the gaseous discharge in terabecquerels per annum versus the limit. And we can see that the activity which was released for those years, 2021 to 2024, was below the limit, and so no regulatory intervention was required. Next, I'm going to go to the dose to the workers and the public, and similar to the waste generation, SAFARI must submit. So they must submit the results of the dose as well to the nuclear regulator. So the first graph shows the average effective dose received by workers versus the limit, and this is for the NEXA operations, not just SAFARI, and this is versus the limit in millisieverts per annum. And the one at the bottom shows these values in greater detail, and the max dose received in these years was less than 10%. This is also from 2021 to 2024. Next is the public dose due to gaseous discharge, and this is again, firstly, showing the dose received by the public due to gaseous discharge from SAFARI in particular versus the limit in terabecquerels per annum, and the one at the bottom shows in greater detail. And with these years, we see that the maximum dose that was received was less than 0.5% of the limit. So next I'll discuss the trends and key takeaways with regards to the NNR. So the NNR is, the strengths that the NNR has is that they have a robust legal and regulatory framework, which is anchored in the NNR Act, as I mentioned before, and there is an alignment with IAEA safety standards, which ensure international credibility. There is also effective oversight mechanisms, which include comprehensive inspection programs and document reviews. Some challenges that the NNR faces is reliance on data given by the licensee, which means that there's no real-time access to data, which essentially means that there's a lag in the enforcement applied by the NNR. And then the regulatory activities may also be limited by budget and staff complement, and the NNR also might need more advanced tools to analyze safety, performance, and predict trends. Future priorities for the NNR are digital transformation of oversight, which essentially means implementing digital tools for real-time monitoring, data analytics, and predictable safety assessment, and also seeking to enhance training and capacity building. Thank you.
Thank you for the interesting presentation. Please note your questions, and at the end of the session, they will be answered. We want to move to our next presenter, who will speak on experience feedback gained from conducting self-assessment of the Trigger Mark II research reactor safety. That is by Jraoud Abdel Jadil. Please, you have 15 minutes.
Okay, thank you. Good afternoon, ladies and gentlemen. So this is the last presentation before lunch. I will try to do it in a manner that you have your lunch as soon as possible. So this presentation, it concerns the experience feedback we learned from performing the self-safety assessment of our Trigger Mark II research reactor. So I will meet it on behalf of my colleagues Bilal Bakari and Shafiq Al-Yunusi. The main content of this presentation, I will give an overview about the CNSTEN, what is CNSTEN, an idea about the self-assessment project in terms of the preparation and how we conduct that project. Examples of some review with topics. I will give just one topic that concerns the Reactor Safety and Security Committee. Another slide is about the safety review mission, and mainly the last INSAR mission we conducted in Morocco. We received in Morocco, organized by the IAEA from 10 to 14 November this year. So the CNSTEN is the Moroccan National Center for Nuclear Energy Science and Technology. It's a public institution. It was established in 1986. And it has triple missions. The first one is to promote nuclear scientific research and applications in socioeconomic fields, contribute to the development of the infrastructure to prepare for an eventual NPP program. We play also a role as a technical support organization to the state in terms of nuclear and radiological safety and security. And also we are in charge of the management of radioactive waste generated at the national level. In order to perform that activities or that missions, we are operating the Ma'mara Nuclear Research Center. Is about 25 kilometers far from Rabat, the capital of the kingdom. So the main facilities of that research center, we have the research reactor. It's a 2 megawatts Trigger Mark II research reactor, constructed by the American company General Atomics. And we have other buildings that had been constructed previously by the French company Technical Atom. So we have other buildings that deal with different activities covering life science, earth science, safety security, industrial applications, and the waste management. KNSTN also, we play a role as technical support organization to the state. So we support national authorities in the review regulations on nuclear and radiological safety and security. We are also acting as active members of 2 national commissions regarding the import and export of dual-use equipment, and also we support the national efforts in terms of emergency preparedness and response. So we host in our facility the Technical Crisis Center. So this is some areas in which KNSTN is recognized at national, at the regional, sorry, and international level. So the self-assessment project. So the self-assessment project, we started it and we conducted it because we had to prepare the INSAR mission. We hosted this month. And that self-assessment project has main objective is to verify, to check the safety status of the facility and to verify the compliance of the operation of that facility against national regulations as well as the IAEA safety standards, and to identify areas for improvement and the related corrective actions. So we rely mainly on national regulations, and also the IAEA safety requirements is artery which has been presented by Farhana. So as I mentioned, so the self-safety assessment allowed us to host the IAEA INSAR mission. The reviewed topics concerns the different areas, starting by the operating organization and reactor management, safety committee, training and qualification of reactor operators, safety analysis, operating limits and conditions, management system, conduct of operation, and other different areas related to the safety. So every topic has been reviewed by an established and dedicated working group that worked on the review of the topics according to national regulation as well as the IAEA safety standards. What are the main steps of that project? We had conducted the project following military steps. The first one is the step of the preparation. We identify the working group members for each modules, or for each module or each topic. For example, for the maintenance, we have persons that are concerned by establishing a maintenance program and performing maintenance activities. And we identify or we select the related regulations and the safety standards. This is the first step. The second step is that we provide responses to the questions to have an idea about the safety status of the facility, and that questions are included in on one of the IAEA guidance is number 35, presented also by Farhana. And the third stage, it concerns the analysis of response. So we investigate, identify the gaps, and we made recommendations for improvement. Example of reviewed topics. So one of reviewed topic is that we reviewed the reactor safety committee. So at KNSTN we have the reactor safety and the security committee, and we review the activities of that committee by following the questionnaire, which included in Appendix 10 of the IAEA Service Series number 35. The reference standards was included by it was the IASR 3, mainly the requirement 6, that sets forth conditions regarding the reactor safety committee. With the reviewed documents, it had been mainly the terms of reference, because at KNSTN we have what we called KNSTN safety and security internal rules, and among that instructions, there is a document that constitutes terms of reference of the Reactor Safety and Security Committee. So the Reactor Safety and Security Committee, it reviewed the different aspects. It has been made according to the IAS safety standards, the requirement 6, and this is the items that are reviewed by that committee. Safety document, safety file prepared for experiments, safety report submitted to our regulator, and so on. So in Appendix 10 of the IA guidance number 35, there is a questionnaire about the safety committee. So we had to answer each question, and for the response we have to provide, of course, the evidence. So the question is there an established safety committee or an equivalent advisory group to review safety aspects of the operation of the research reactor and its related facilities? The points that have been taken into consideration, they are listed here. The references, as I mentioned, are 3, and the evidence, the documents that we had been reviewed, the safety committee terms of reference, and records of the safety committee meetings. So we analyzed, we had now comments because we are in compliance, we meet the requirements subject to this question. For the second question about the safety committee, so we answered the guide, and we found that we had to include in our review, in the review topics by the safety committee, the radiation protection program. So this is the recommendation that had been issued from the analysis. So the same thing had been done for the other different areas, maintenance program, training and qualification, and so on. So after performing the safety assessment, we prepare a report that includes all the questionnaires, all the questions and their corresponding answers, and we submit it to the IA expert before conducting the INSAR mission. So for the safety review mission, the INSAR, so as I mentioned, we received that mission from 10 to 14 November 2025, and it covered the different areas that had been agreed with the IA during a pre-INSAR mission that we organized in 2024. So the IA identified the areas that are in line with the IA safety standards, and also identified some areas for improvement, and identified some good areas, such as that the fact that the reactor safety and the security committee, there is a security committee included in the safety committee in order to avoid any conflicts between both components, safety and security of the research reactor. So there is the press release, the link is here. So the IA finds continue with improvement at the Trigger Mark II research reactor. So in terms of the conclusion, the self-assessment project, its preparation and its conduct has been very important for us in my institution. It was an important tool to strengthen the safety of the research reactor. The use of the IA safety standards and guidelines had played a key role on the performance of the self-assessment projects, such as the questionnaire included in IA Guide number 35. The involvement of young staff in that project had been a key component for the knowledge transfer to that young generation. And also, I would like to highlight the organization of the lifetime of our research reactor of peer review missions, including mainly those organized by the IEA. So thank you so much for your attention. I will be glad to take your questions. Thank you so much.
Thank you so much, Raoult, for the interesting presentation. So we have, do we have, yes?
speaker yesterday, I think it was Ahmed, I don't know if he's in the audience and
Yes.
prepared to talk.
More. Yeah, please, are you ready? Okay. So we want to take Sahi, this is Sahi, Mohammed Sahi, who will speak on safety-linked SSC's integrity control, actual and prospected plan. So let's welcome Sahi.
I am pleased to present work about safety-linked SSC's integrity control, actual and prospective plane. In principle, nuclear process are designed so that the facility in use maintain the reliability requested in the safety cases, thus ensuring that the hazard presented and the associated risks are kept at low as possible. The reliability of the facility must be assured throughout its life cycle via adequate attention and understanding of SSC's behavior, mainly those directly related to the safety. Identification and categorization of safety functions according to postulate-initiated event using the ID approach and graded approach are mainly considered in the classification of SSCs. So supervision and integrity control of SLM research reactor SSCs is carried out based on the following regulating and technical framework as national regulatory framework, EAA safety standard, as mentioned Mr. Malaka and all lecturers, the management system throughout operational requirement, throughout modernization and refurbishment of SSCs, and taking in consideration human resource capacity or qualification. And we must have technical support and partners to follow up SSC's integrity control. So I go throughout one by one to explain our approach. So before I give some review of a SLM research reactor is heavy water research reactor. Is first criticalities in February 1992. Its instrumentation, AC, electrical, and dosimetric system were modernized between 2011 and 2015 and 2019. So the reactor is tank type research reactor of 15 megawatt power, cooled and moderated by heavy water using graphite as reflector. They have a lot of facilities around the research reactor to support R&D and laboratories around. We have a lot of for neutron scattering, neutron imaging, LAA with different methods. So for the product and services of a SLM research reactor is dedicated to radiation production of radioisotope, scientific research, material testing, and training of technical and scientific personnel. So for the first point to support our follow-up of SSC's component of the SLM research reactor is a national regulatory framework. We have nuclear law promulgated in 2019. First chapter of this law is establishment of independent national authority of nuclear safety and security and its mission. The authority was established and it's operational since 2021. Other chapter described activities on nuclear safety and nuclear facilities in Article 19 to 22 and in Section 4 for operation. So this article or chapter are among general integrated provision to ensure safety operation during life cycle of nuclear facilities by requiring for organization operation. So the requirement is we must have validated management system, updated regulatory document, validation program, different program for maintenance, inspection, control, and we must have technical support and human resource qualification. So application text of the authority, national authority, is under approbation by the government. So from regulation point of view, integrity and the control of SSC's nuclear facilities, during their life cycle are required. For the IAEA safety standard, there are a lot of tools, a lot of standards to support member state to conduct. So we use you use safety standard and guides regard and first reference to develop our regulation and adopt prescription which lead to the safety enhancement of research reactors such as SF1, SSR3, SSSG, differential, and SRS99, GSR Part 1, GSR Part 2 to develop our program to control the SSCs. So IAEA support above contribute as mentioned by Farhana. There are other tools to develop this plane. So IAEA support above contribute to acquire competence to improve safety throughout control of the integrity of the SSCs. The third point is it's the management system. We are developing this management system. Our management system is progressed in 3 phases. The first phase, quality assurance program is provided with the installation of all life cycle of the reactor. After the modernization of the project, we moved to an integrated management system. The second phase in 2012, the management system is focalized in ISO 40001. What the focal point is the services, is not the safety. So the third phase is after modernization of the reactor, in 2023, Commissioner decision implementation of EMS of Salam Research Reactor based on GSR Part 2, selected as basis standard. Appointment of project leader and project team, and especially we're working on an internal audit, what is existing vs GSR Part 2, establishment of checklist, and self-assessment according to establishment checklist. So we do some development of documentation, and we identify core processes of our IMS system is operation, maintenance, and management. So we pass to classify the SSCs according to safety, quality, earthquake. SSCs technical documents are under development. So we consider 17 safety functions are used to classify SSCs. So I give here an example of one system of 20 systems. Each systems include a lot of components. As said, we must have more than 1,000 components. And each component must be identified with detailed information. So for the primary circuit, we take a principal component, reactor vessel, pipe of primary circuit with different diameter, main valves of primary circuit, primary pumps, and primary heat exchanger, and we classify for 5 classifications: safety classification, safety function, design manufacturing class, and QA class, and seismic class. So each, as I said, each component, we must have a technical document about its function, all documentation related to this component, different documentation for safety analysis report, transfer technology, lot of demand, design, detailed design, etc. So we have also information of the design, information about operation, information about maintenance, and feedback experience of operation. And we have also for this technical document fault historic of preventive maintenance on the component, historic of predictive and preventive maintenance, and operation hour of each component. So for operation requirements for the follow-up the SSCs of a Salam Research Reactor, we have 3 programs, operation programs, we have a maintenance program, and a technical management program. Each program takes care of the behavior of SSCs. So for modernization and refurbishment of the reactor, SSCs of Salam Research Reactor being in operation since 1992 have experienced equipment failure, component obsolescence, availability of spare part, and aging effect due to the degradation of physical properties over time and operational condition. So for addressing these issues, an in-depth assessment of SSCs is conducted by the OO. It leads to conduct a modernization and refurbishment project between 2015 and 2019, mainly involves reactor AC systems, new main control room, auxiliary control room, electrical power supply system, normal and emergency, new digital control system, and radiological monitor system. The new digital control system is very good tools to follow up SSC's behavior. So the OO operation and maintenance staff took part in the phases important of the design, installation, and commissioning of this project. So human interaction with machine is very important to follow SSCs. For human resource qualification, we have procedure to qualify our personnel of operation or maintenance staff. So we do training and qualification of operator and maintenance staff was allotted to Algerian Institute for Nuclear Engineering Training after recruitment by OO, which is done according to procedure. TQ programs are elaborated by pedagogy committees and validated by the national authority. Those programs are designed to enable candidates to acquire both the perfect understanding of the reactor theoretical basis as well as practical training necessary. We conduct this training on 3 parts, theoretical part, specific training, and internship to perform function during 1 quadrimester. The success on TUK phase is required to postulate the operation and maintenance license, which is delivered by the national authority for 3 years renewable. A process to obtain license is a criteria of admissibility, requirement of technical license, exams written, and practical exams, the amount of technical license by the OO. So we have another program for training with the collaboration of the OO EAGM take in charge the continuing and refresh training for improving capability skills to fill any gaps recorded and to maintain acceptable level of competence. So for technical support and partners is also important to follow up the SSCs. The OO has an organization based on hierarchical structure and support committees. So we have reactor unit in charge of operation maintenance in accordance with OLCs and approved procedure. This under the supervision of reactor director. Reactor director is accountable to the DG, nuclear safety. 2 minutes, yes, okay. Nuclear safety and radiation protection unit, safety committee, multidisciplinary technical team, QA unit linked directly to DG, and reactor utilization committee. So for technical support also and partner, we have Research Center on Industrial Technology, CRT, to support NTD inspection. So for prospected plane, we project to achieve the IMS project, and we are developing aging management program is under development, overview and concept. So we have a requirement and safety standard, collect all regulation. We collect data and information required during the nuclear installation lifetime. Main factor considered integrated management system and technical group to validate aging management program. And we use also international experience to develop and enhance our program. So this is some technical e-service inspection technique that recently introduced in our program. Also, offline monitoring of reactor fluid, also TAA, prognostic on and health management to evaluate LTA lifetime of SSEs. We have physical integrity verification of Salam Trout radionuclide measurement is under consideration. We have a technical group to do some technical calculation about the vessel mechanical behavior and cracking factor. So in conclusion, since its criticality, Salam reactor has been operating safely and reliability due to the set of comprehensive operating process. Additional measures have been considered by the OO to further improve safety and ensure control of integrity of SSEs. Thank you.
We have one more presentation before lunch, and so we want to take that from Hassan Mansour. If Hassan is here, he will present on enhancing nuclear reactor operations through QR code-based equipment labeling system. Hassan, please, you are between us and lunch, so please make it.
Okay, I will try.
Thank you.
Okay. Good afternoon, ladies and gentlemen. My name is Hassan from Tajura Nuclear Research. From Tajura Nuclear Research Center, Libya. My presentation is about simple idea QR code. We already use it in daily our life, which is give us fast, safe, and secure access to the data and information. This idea is currently under implementation at our nuclear facility to facilitate our work. Okay, nuclear facility are inherently complex, comprising numerous vital safety system, in addition to auxiliary system necessary for reliable operation. Their safe, efficient functioning require highly qualified and disciplined personnel supported by effective tools and facility daily activities. Simplifying operation process not only enhance the efficiency of routine maintenance and periodic safety review, but also improve overall emergency preparedness support, aging management strategies, and strength reactor safety assessment and review. The goal of our work is to introduce simple, modern, and low-cost digital tools that can significantly enhance operation efficiency, maintenance, reliable knowledge management, and emergency preparedness. Before moving forward, it's important to briefly explain what QR code is. QR code is a quick response code. It's two-dimensional barcode invented in 1994 by Japanese company called DenseWave. It can store more than 4,000 alphanumeric characters, which hundreds of times more than traditional barcode, and can scan it instantly from any direction, even if it's dirty or partially damaged. This makes it very fast, reliable, and flexible tool linking physical equipment to digital information. Every day in 2024, people around the world can scan more than 2.9 billion QR codes. QR code technology is not unfamiliar to us. We use them to access bank account, health records, flight boarding passes, food ordering, parcel tracking. This is how we work today. We often need to search through maps and documents manual just to understand system, solving problem, or perform maintenance. These documents can be lost, damaged, becomes outdated, or difficult to access, especially in urgent situation. On the right photo, this is how we can work tomorrow. By scanning single QR code, all technical information becomes immediately available, like equipment history, maintenance records, maps, manual, and operation data. That reduces time, avoid mistakes, and makes entire process faster and more reliable. The system proposed for our facility follows three-layer structure. The first layer is a physical layer. We print or laser engrave durable QR tags on stainless steel or aluminum plates. These tags are designed to survive radiation, high temperature, chemicals, and year of cleaning. Application layer, which is the core of the digital system. This layer includes secure web server connected to database that store all related information. Whenever QR code is scanned, the system retrieves data directly. A client layer using secure mobile device such as tablets or smartphone, they can scan QR and immediately retrieve information they need from the database. QR tag specification withstand demanding environmental condition of nuclear facilities constructed from durable materials, including stainless steel or aluminum, guarantee reliable performance through their operational lifespan. Security framework, the entire system operates inside the internal network of the reactor, fully isolated from the internet. Only authorized personnel can access, and all activities are controlled and logged. Implementation strategy, we divided our project to three phases. Pilot phase, we'll focus in critical system. We selected two critical systems, primary cooling system, main control rooms, and instrumentation panels. We allow the testing and refinement based on real world feedback. Scale-up phase, extending the system coverage to encompass all safety critical equipment through the facility. The last one, for full deployment stage. Expected performance metrics. These numbers have already been achieved with the pilot. Average time average information access time was reduced from 10.2 minutes to just 1.3 minutes. This is 87% improvement, meaning our staff will spend their solving problem instead of our searching for information. Documentation error reduced by almost 99%. The maintenance delay due to the documentation, over 56% delay will be eliminated. Emergency response time is improvement about 30 and the training time for new staff is reduced from 6 weeks to 2 weeks. Benefit and impact assessment, operation efficiency, facilitate immediate access to comprehensive equipment history and technical specification. There be significantly reduce maintenance downtime and enable more efficient scheduling of operational activities. Furthermore, the system enhance equipment traceability throughout its entire life cycle, providing robust function for strategic asset management and long-term operation planning. Safety enhancement provide rapid access to critical emergency procedure during incident response scenarios, substantially improving compliance with established safety protocol and regulatory requirements. Capable ensure better preparedness for regulatory audits and strengthen the overall safety culture within the facility by providing authorized personnel with instant access to verified safety information when it's most needed. Knowledge management, this system serves as a vital mechanism for preserving institutional knowledge and mitigating the impact of staff turnover. Streamline the training process for new personnel through standardized, sustainable framework for knowledge retention and transfer. Conclusion, the Tajura Research Reactor, commissioned in 1983, consists of numerous complex systems that require precise management and to ensure safety, efficiency operation. This QR code gives us faster and more than reliable maintenance, quicker and more accurate emergency response, better preparation for aging management, and most important, live digital memory that will protect our reactor for a long time. Thank you.
Thank you for the interesting presentation. We have time for 2 to 3 questions. And so all our speakers are here. Farhana is here, Sami is here, and all the others are here. NNR are also here. So 2 to 3 questions. I think I saw your hand first, followed by you. And then, yes, so.
Thank you. My question is for NRR participants. I have a question related to the approach for potential exposures, no? The criteria or the acceptance criteria for accidents in MPP and the difference between MPP and research reactor. Thank you. I mean, is there a kind of limit risk approach or something like that?
Yes, can you pass the mic behind you?
Yes, we do. We have published a regulation 388 as presented there. Actually, the presentation, the version of the presentation, I think it was the first draft that we have sent. Actually, we did put the doses and the limits for which we regulate these 2 facilities, the NPP as well as the research reactor. Yeah, we do look at the accident and the response, whereby you actually look at the benefit versus the risk in terms of emergency interventions. Yes, we do. Yeah, as much as I said, it is indicated in the regulation, R338. If you go at the back, you will get all the limits in terms of the intervention. Even NEXA have already, in terms of their process-based, define the interventions in terms of an accident. And we have accepted their process-based documentation.
Sorry, the design. How do you establish an acceptance criteria for a new research reactor, a new project, in order to assess the design?
Okay.
To approve new designs or something like that?
Yeah, we do have position papers at the NNR to look at the SSMR, the Quebec, as well as the MPR, as much as we are going to license the MPR. There are already documentation that we have already developed on each aspect. Those documents we publish on the website. If you go to the website, you will get regulation rights, as well as concerns and assessment that we have. Regulation to not ensure and have everything, and then forces us to develop regulation rights. At the moment, we have the new method that is problematic, and then the regulations that are currently under the process. But the private documents, especially the regulatory ones, is the regulations that are problematic. Because we really want to wait for the implementation, so that we can actually do the purposes. The problem was that the NNR Act, when it was revised, it took too long to get. Actually, it was allocated to ACC, and then the regulation established about we could use it as a template regulation for the implemented, because of the fact that that was the record of those regulations. Now go through the review process, go to Parliament, and then to implement it. At the moment, we are still sitting with the approval process by the agency for what and then go to Parliament.
Thank you. Please, next question.
Thank you. My question is to Mr. Salim. Considering that Safari is doing this LTO, on your page 5 slide, I'm assuming when you say LTO, we're talking about the plan definition design that we need to do now, right? Supposed to under LTO. Your slide mentions that the Safari regs does not have the design policy life. Is that even to the operational life that is 6 years? And the second question is in our services combined regulations. On the authorizations process, there was a presentation by the NNR speaker. Under SAR, usually you include previously the facilities process which was included in the SAR, and then you submit sensitivities. But on your presentation, I saw always separate documents. Now the case where the SAR need not to facilitate process description, but it's separate document. I think that the indicator is not really
of Safari. Most of these experiences, they don't have a design, but by using and then they provide sensitivity assessment for the opportunity safe operation. So the authorization of the first assessment it was exposed to us because I believe I'm not looking at it in terms of safety assessment. They said we will clearly do the assessment. So the next period of the assessment should happen of 2020 to give of operation. So I guess the farmers are assessment at the moment. So I think it's not looking at the Safari. What was the experience was child of Safari. Some of them are necessary for 5 years. Thank you.
My name is a question to Hannah. Still to Hannah, so you can find the question. So, in Kenya, we are currently developing regulations for plants and reactors. And developing these regulations is the responsibility of national environmental regulator and so especially the nuclear part of society and such and then relationship where they really like nuclear relations, but we have a site. They get a good one of those experience, then they will look at the acts, has something to do with the environment, first of all, relationships can come in. So this was one of the
operations with respect to this risk. Because this is a delicate exemption. You are reading your original facility whether you exempt you from the expected costs and you meet the exemption level. But by specific meaning of authorization, we still have expectancy, we still have social compliance, implementation compliance with exemption costs, as well as the exercises as well as the priorities. Thank you. Thank you. We want to conclude now. We want to conclude. We can continue the discussion at lunch and after questions at lunch. I made a few points here that safety remains a key factor with respect to approaching standardization, and we can come on the emphasize that point. We also must make use of IAEA services expectations to enhance safety in our facilities. And finally, I said that continuous learning through collaboration like we are having in other projects is key to enhancing safety performance at our facilities. With that, I thank you for your audience and for your participation.